welcome to the first annual International 2023 online Echometer training course. We really expect that these next 3 days are going to be very action-packed and full of information that, day one, we're going to cover liquid levels. Day two, we're going to cover dynamometers. And day three, we're going to end up covering gas lift, gas wells, as well as the dual shot and plunger lift. So we have a lot of information that we're going to be throwing at you over the next 3 days. And we really hope that you enjoy this online training course. And hopefully with the growing participation, we'll continue to be able to do this in the future. Now, one of the things that we wanted to start off doing is that we feel that it's very important that you know where you have access to resources for Echometer Company. And so the first thing we wanted to start out by doing was introduce you to our website and just inform you and let you know where you can find key documents as well as other online trainings that may be able to assist you as you continue to learn and grow and develop your skills in utilizing the Echometer equipment. So the first thing I want to do is I want to introduce you to the website. Now, the website is www.echometer.com, as you can see is the top of the URL. Now, to navigate to the website, you'll see across the top of the home page, we have several different options, starting with products. Now, one of the things that's not commonly known to our users is that on our website, we actually have access and diagrams to any piece of equipment that we manufacture. This can be very beneficial when you're out in the field and you're having to tear down one of the wellhead attachments or one of the gas guns, that you can open up the PDF document and reference the particular serial numbers for O-rings and different mechanical parts whenever you're tearing your gun apart in order to replace components in the field. So in order to navigate to any of these particular gun types, you can navigate to our website, echometer.com, go to products, and navigate to gas guns. By selecting gas guns, you will see many of the different guns that we produce and manufacture here at Echometer. One of the guns that we'll be talking about today in today's session is the wireless remote fire gas gun. If you select the type of gun that you're interested in, you will see the features and the unique specifications related to that gun. Towards the bottom, you will see where you can view the PDF drawing, and by simply clicking on the embedded link, you can open the exact gun drawing that will be referenced to particular component as well as Echometer part number. In the event that you need to order any of these particular components, when you send an email to Gustavo or myself or the Echometer sales department, you will be able to reference that particular number. And so that way we can make sure we get you the proper component in order to get you up and running. Now, the website is full of different information, one of which being different software downloads. As you know, Echometer software is free to download. And so if you're interested in downloading the TAM software, our latest version of Echometer software, you can go on the website and select the different modules and download the software directly from the website. We also have other versions of software on there, such as Total Well Management, TWM, as well as AWP, QROD, and the gas separator simulator. There's a lot of information on the website. One of the things that we're most proud of is the Ask Echometer session. During COVID, when we were unable to travel and go out and meet with you guys and attend different trainings in person, we created 23 online sessions which are free to view, covering a variety of different topics that you may find interesting. So as you go through these 23 online topics, you can see, such as session 23, identifying holes in tubing and sucker rod lifted wells. Go through, take a look at the different sessions and see which one fits your unique needs, in which you can determine that you would like to spend time and invest a little bit in yourself and your practices as far as analyzing and troubleshooting Echometer data. You will also find plenty of technical papers, as Echometer has partnered in many hundreds of technical papers over the years. You will also be able to find a link to the training that we host here in the US that is free to attend. We would recommend that if you can make any of these trainings, they are great trainings where we can meet in person and go through and discuss specific topics, as well as set aside time to discuss your unique data. So with that being said, we think this is a great introduction as to where you can find these particular components and these particular things from the website. How we want to get this started is we would like to get you started with understanding how to utilize the TAMS software, and we're going to create a base well file. And so with that being said, I'm going to kick us off with our first video. Hope you enjoy.
This video will cover the software essentials for create a well file in TAMS. First, we must create a well file. From Pick a Well, click Create. Type in the well name and select a group from the drop-down or create a new group to place your well. As you can see, there are many templates you can choose from to start building your well file. For this example, we will use the basic rod pump template. Notice at the top we have Quick View and Detailed View. Use Quick View first to lay the framework for your well file. I will go through and add some values for our example well. You do not need to fill out every field, and you can always come back to add information at a later time. One of the most important and often overlooked numbers is average tubing joint length. We use 31.7 feet per joint as a default value, but if possible, use the average specific to your well. This is a key variable in calculating distance to liquid using the collar count method. Be as detailed and as accurate as you can when creating your well file. The better info you put in, the better results you will get out. We will now skip ahead and look at the detailed view of the well profile. In the Well Conditions tab, you will find your production table. This is a nice piece of information to keep in the well file. It is also essential information if you wish to take static shots and calculate static bottom hole pressures. Notice that most of the mechanical wellbore tab is already filled in. We filled in this information in the quick view earlier. This is a good place to double check and make sure all the values you used are correct. Next, we have the Lift System tab. For our purposes of setting up for a liquid level test, there are not many essential variables here. However, if you plan on acquiring dynamometer data, this tab is extremely important. The one variable we want to double check here is pump intake depth. In order to calculate an accurate pump intake pressure, the pump intake depth must be correct. Next up is the Survey tab. Here you can copy and paste or type in measured depth versus true vertical depth. If you have a deviated or horizontal well, this tab must be filled out in order for the program to calculate accurate pressures. In the Producing Interval tab, you can add multiple sets of perforations to your well file. At the bottom of this tab, select what depth you would like the program to calculate your bottom hole pressure. The Tubular Markers tab will already be populated with information that we have previously filled out. Feel free to add any further information you would like. And lastly, the Well Description tab gives you a place to add more identification details for your well. Don't forget to save all the changes you've made to your well profile.
So we wanted to introduce how to create a well file because it's very important prior to getting out to the field that you create your well file with as much detail as you have. Ultimately, I know that sometimes having well information is hard to come by, especially if you are a third-party operator that is utilizing incomplete records to generate these base well files in TAM. However, do the best that you can so that way you can ultimately have so that you can give the operator and yourself a clear picture of what is happening in your well. If you have further questions about that, please direct them in the chat so that we can answer them at the end of this session. So that way we can make sure that we can answer any questions that you may have. Now, what we're going to be doing next is the next two steps are including testing your equipment ultimately before you get it out to the well. It is important that we make sure we function test the equipment prior to going to the field, so that way we don't have any surprises or hiccups once we get out in the field that will ultimately leave us without being able to acquire the data. Okay, so the next video is ultimately one on utilizing TAM 1856 to set up the sensors as well as to test the hardware. Now, we will be utilizing the wireless remote fire gas gun, the wireless pressure transducer, as well as the wireless PRT. So there are some sensors in here that you will not be related to shooting fluid levels. However, we will be covering them in the coming days. So with that, I'm going to be speaking through this video because there is no audio. So the first thing we're going to do is we're going to turn on our laptop computer and then ultimately connect our wireless base station. Now, when you connect your wireless base station to your computer, you should hear the audible noise from the base station connecting. We're going to turn on our individual sensors. Now, notice as we turn on our individual sensors, as we push the power button, you see a sequence of green, red, and then a number of green blinks. Those number of green blinks are equal to the battery percentage of the individual sensor. When opening TAM, we're going to go to Setup Hardware in the top left-hand corner, and we're going to select Base from the dropdown because that is ultimately what we're going to be using for the wireless sensors. From here, we'll be able to click on Discover Sensors with the sensors on, and you can see the sensors have appeared as well as their signal strength and battery percentage. And we're going to end up pairing each individual sensor to the base station. Now, you only have to do this once, similar to pairing your phone to the Bluetooth in your vehicle. You only have to pair it one time, and once the sensors are paired, okay? Now, I'm going to pause the video for just a second because one of the things that's important that I want to distinguish between the use of wired equipment and wireless equipment. With the wireless equipment, the coefficients are actually saved inside the board. And so whenever you pair the equipment to the base station in TAM, the coefficients are automatically going to come over and they're going to populate. Now, you see that the particular sensor that I have displayed at this point is a WPRT, or wireless polished rod transducer, which is used in the acquisition of dynamometer data. Now, this particular sensor only requires a C2 and a C6 coefficient. The information is automatically pulled in to TAM from the board. Now, if you have wired equipment, when you set up a brand new sensor, you need to make sure you go in and you manually enter in the coefficients as printed on the transducer or as printed on the WPRT. Whatever sensor you have, you need to enter in those coefficients and save those coefficients as you build out the individual sensors. Okay. And one of the things that we'll see and we'll introduce is that if you're utilizing a well analyzer and not a base station and wireless equipment, you can go to the select hardware and you can use the drop down and select well analyzer versus the base station. Okay. And ultimately build your sensors into whatever method or whatever piece of equipment that you're using to acquire the fluid level data. So Important note, always make sure that the coefficients are entered in. It'll come over automatically if you're using wireless. You'll have to enter them manually if you're using the well analyzer in the wired equipment. Now, we want to obtain a zero offset on the sensors prior to acquiring the data. Now, the zero offset is going to be required on the pressure transducers, which will ultimately which will be a part of the wireless remote fire gas gun, or the pressure transducer that manually attaches to the wellhead attachment. Also, with the wireless pressure transducer, you want to make sure that you get those zero offsets prior to acquiring data. Now, some people ask, how often do I need to get my zero offset? It's common practice for me that I get a zero offset on each well that I go to. As I go throughout the day and the temperature changes, I want to make sure that I have an accurate zero offset. And that zero offset, as we're about to see in the coming slides, that zero offset is going to be conducted with no pressure on the transducer. The well will be closed, the valve will be open, and the pressure on the transducer will be reading atmospheric pressure. You do not want to zero the pressure transducer with pressure on it. Same with the WHT, which stands for wireless horseshoe transducer, used in dynamometer acquisition, or the HT, the wired transducer. You do not want to zero the offset with load on the sensor, on the strain gauges. So here you can see we've selected our sensor. Once again, there is no pressure on the sensor at this time. If you zero the sensor with pressure on it, it will mess up the data, and it won't mess up the data, but it will mess up the zero offset on the pressure transducer. So zero the pressure transducer with no pressure on it. We're going to click Get New Offset. Once we're satisfied with the offset, we're going to click Use Shown Value, and you can see how that ultimately shifted the value over to the last offset. And now we're going to demonstrate doing the zero offset on the wireless pressure transducer as well. So once we've done this, the hardware setup has been. Now, these were all essential steps on creating a well file in the office, and then checking the function of your hardware, setting up the hardware, making sure things are connected, making sure the proper coefficients have come over, everything was taken care of. Now, let's venture out to the field, and what we're going to do is we're going to go through the procedure on how to acquire the basic steps for shooting a liquid level utilizing the TAM software. What you're going to see is that a lot of these steps are very similar to the same way that you ultimately set up the hardware in the office. Number one, we're going to open the TAM software, and we're going to plug in the USB cable from the base station. This is commonly referred to as the wireless base station, and it connects with a cable that has a USB-A connection to the laptop and a Thunderbolt connection or printer connection to the back of the wireless base station. So we're going to start the TAM software and plug in the USB cable. Step one. Step two, because we've already created our well by going through and creating a well, we're going to be able to go in and select Pick Well located at the top left of the TAM screen. We're then going to be able to navigate to the particular well that we've created. Okay. Once we navigate to that well, we can select it by either double clicking on the well or going and clicking on the load button. Once we've done this, we're going to attach the Echometer gas gun to the well. Now, this is important because this is where it comes into the safety of the attaching of the gun. We ultimately want to remove the bull plug, making sure that there's no pressure trapped between the bull plug and the valve, bleed off any excess pressure between a closed valve and where you plan on installing the gun prior to installing the gun. We're going to check the threads. Now, the threads are a 2-inch NPT. We're going to check the threads for valves and corrosion, make sure there's no wear or damage that would ultimately allow the gun to have a bad connection that we could risk the pressure blowing the gun off of the wellhead. Now, we want to make sure that we apply Teflon tape to the mic protector on the base of the gun. This is commonly referred to as the mic protector. And when we install the gun to the wellhead, we want to make sure that we're going to make 4.5 turns in order to promote a safe connection. We do not recommend using any type of quick connects to the wellhead. We do recommend making that 4.5 turn rotation in order to have a safe connection to the well. As we indicate, less turns may indicate that the threads may be damaged, there may be galling, there may be issues that where you would not want to take a fluid level shot on this particular well. Now, this is where we're going to turn on our remote fire gas gun. We're going to do that by pressing the power button. And as we saw in the setup hardware video, it's going to flash green, then red, and then green for the number of flashes equal the battery percentage on each sensor. Ensure prior to going out to the field that your sensors are charged so you don't come home empty-handed with no data. So we're going to click on Setup Hardware in the top left-hand corner, and we're going to select Base because we are utilizing the wireless equipment. Now, as I alluded to, if we were using the well analyzer, the wired equipment, we would make sure to choose well analyzer from the drop-down. However, in this example, we're going to use Base because we're using wireless equipment. Once we select Setup Hardware and connect to the base, and the gun has already been turned on in a prior step, you can see that because we did the complete hardware setup at the office, the gun is already a friendly sensor to the base station. And so the gun will automatically appear in the sensor list here to the left. Now, if it doesn't appear, you're going to go through the steps of discovering the sensors and pairing the sensor, as we saw in the complete hardware video. However, it's already paired, and so we have the ability to perform offset. As I was speaking of earlier, we want to make sure that we obtain the zero offset with no pressure on the sensor. In our case, using the wireless remote fire gas gun, we're going to make sure that the valve is closed to the wellhead, the gun is attached to the wellhead, and we're going to open the valve on the side of the gun, which is called the bleed valve, ensuring that that pressure transducer is subjected to zero pressure or atmospheric pressure prior to getting the offset. We're going to select Perform Offset. Once the offset stabilizes, we're going to lock in that value by using Shown Value. Now, because we're performing a liquid level test, we're going to go up and now click on Liquid Level Module. By clicking on the liquid level module, that is going to give us the options to perform the liquid level test. It's important when acquiring data with the Echometer sensors that all of your tools in which you'll be using are selected at the top of the toolbar. So if your gun is not present with a green check mark next to it, it's important that you go to the right and select Pick a Sensor and select the appropriate sensor in which you plan to do the acquisition with. You can see in this case, we will be using the WRFG 2451 for this acquisition. Now, we're going to prepare to shoot the well. In some of these details, we will go in further during the discussion on direction of kick, as well as shooting wells later in this session. So step one, we're going to charge the gas gun 150 to 300 PSI over the wellhead pressure, okay? We're going to charge the gun before we open the well, subjecting the well pressure to the gun to ensure we don't have trash and debris enter in the volume chamber and ultimately give us increased maintenance issues. Charge the gun first. We're going to close the bleed valve on the side of the gun. As you can see here, this is the bleed valve that I was referring to. We're going to close it so that way when we open the wellhead pressure, it does not blow gas outside of the gun. Once this valve is closed, we're going to open the ball valve downstream of the gun, subjecting the gun to wellhead pressure. And then we're going to close the casing valve to the flow line. So we're going to close the casing valve on the back side of the wellhead, ensuring that when we fire the shot, the pressure wave is only allowed to travel down the well, and ultimately not out through the flow line. Okay, so we're isolating the path in which that wave can travel. Now, the quick release of the gas is what causes the pressure change, which is going to generate the pulse, which we can ultimately use a different either collar count, downhole marker, or acoustic velocity to be able to calculate the acoustic velocity and determine the depth of the liquid level. You can either use nitrogen or CO2 gas in order to generate this pulse. So step here, the valve between the gas gun and the annulus still should be closed. Prior to closing the bleed valve, we're going to open the valve, close the flow line on the production side so that we can fire the shot into the well. Here you can see Ken closing the bleed valve. Here he is opening the casing valve between the gun and the wellhead. Now, this is an important point that I want to bring out. Know the casing pressure or whatever path you're shooting prior to installing the gun and opening the valve. All of Echometer's equipment is pressure rated, and it's all stamped on the equipment. If you have a gun that is rated for 1500 psi, know the pressure on the wellhead prior to subjecting that piece of equipment to that pressure. We do not want to overpressure any of the equipment. Make sure that your equipment is sized pressure rating for the pressure you expect to subject to that sensor. Valve is open, gun is downstream. Now we're going to close the valve on the opposite side on the production side of the wellhead to ensure the wave only travels down the wellhead and not out of the flow line. Now, there's different ways with the wireless remote fire gas gun in which to acquire the data. One such way is that you can acquire from the sensor itself. As you can see from the images here, we have our power button, which we've made you familiar with. We also have the acquire button and the fire button. We've already selected the liquid level module, and by simply clicking on the acquire button, that will begin it will make it so that the microphone is listening to the wellbore. Okay. Now, one of the things, once the acquire button stops blinking and you have a solid green light next to the fire button, you can push the fire button and fire the shot from the sensor without ever having to walk back to the computer. Now, if you prefer to go back to the computer, what you can do is instead of clicking fire, you will just on the gun, you actually click take shot on the TAM software. Okay. So as you can see from the TAM software, we actually have step by step the steps that you're going to take prior to firing a shot. Now, one of the things that's very important prior to firing the shot is we want to inspect the well noise that's displayed on the screen prior to firing the shot, just to verify that the instrument is working correctly. If excessive well noise exists, such as pumping unit noise, high gas flow rates, we may want to use a larger charge from the 150 to 300 pounds differential pressure that we spoke about earlier in order to generate a proper acoustic pulse into the wellbore. Now, if we're going to start the acquisition from a laptop, rather than pushing the acquire button on the gun, we're going to be in TAM and we're going to click on the Start New Test button. This serves the same function as clicking the acquire button. From Start New Test, as we've seen, once we charge up the capacitor to the proper voltage we need to open the solenoid, the Take Shot button will be displayed. You can click Take Shot, and that will initiate the acoustic pulse. Now, the way the TAM software is set up is that the acoustic acquisition is going to run 3 seconds per 1,000 feet of perforation depth that you enter in the base well file. Okay. So you will see that when the shot is fired, there will be a message saying acquiring shot, as you can see right here. You will also see a time if the shot is detected in which the acoustic trace will run before automatically going back to the TAM screen. After the data has gone back to the main TAM screen, in which you will see the liquid level module, you'll still see ACQ, which stands for acquiring. And while the sensor is acquiring, what it's doing is it's acquiring a pressure buildup. Okay. It's important. It's an important part of actually calculating the producing bottom hole pressure to allow the sensor to actually acquire this pressure buildup. Now, whenever you do the pressure buildup, we always request that you have at least a 2-minute buildup of good linear measurements. Those measurements in TAM are going to be taken every 5 seconds, allow for a minimum of a 2-minute buildup. But if you need to let the buildup run longer, you sure can. We can actually have a maximum pressure buildup during a liquid level acquisition of up to 15 minutes. Once we are finished with either the 2-minute buildup, which it will prompt you with, do you want to end this pressure buildup? And you can select yes or no, or you manually end the buildup at any time that you want. You can stop the buildup by clicking on end pressure buildup. Okay. Now, at this point, we're going to step into methods of analysis. And I don't want to steal any of Gustavo's thunder. And so I'm not going to hit very much on this because I want Gustavo to be able to speak to you about this in detail. However, I do want to point out that the methods and tools to refine the results are located here at the bottom of the screen, where you can see collar count, downhole marker, as well as acoustic velocity. If you want to generate a PDF report in which you can give to your customers and or put on file for your operations, you can simply go to the report button, which is located near the Start New Test button, and select report, in which it will generate a 1-page PDF report that you can print out or save to your liking. The one thing that I will mention is that make sure that you analyze and select the proper liquid level mark before generating the PDF report. TAM is good, but you need to make sure as an analyst that you go through and you pick the proper liquid level and make sure that things are correct before generating a PDF report, which you cannot change. Now that we've acquired the data, we've ultimately gone through, we've acquired our pressure buildup, we're going to remove the Echometer gas gun from the well. It's important that we follow the steps to ultimately bleed the pressure to isolate the gun from the well and bleed the pressure from the gun prior to removing the gas gun. Trapped pressure will end your day in a hurry and often not in a way that you want. So we're going to turn off the gas gun. We're going to open the bleed valve from the casing to the flow line, restoring production, going to the producing side. Going to close the valve between the gas gun and the casing. We're going to use the bleed valve on the side of the gun to open and bleed the pressure, trap pressure from the gun. Then we're going to remove the gas gun from the wellhead, obviously turning off the laptop computer, and leave the well as we found it, ultimately putting all the valves back in the position that they were prior to acquiring the data. Now, with that being said, we've gone through, we've talked about creating a well file. We've talked about setting up the hardware in the office, bench testing the equipment, and also acquiring a liquid level in TAM utilizing the wireless equipment. With that further ado, now Gustavo is going to take us through the liquid level basics as well as methods of analysis. Thank you guys for your time.
Thank you, Justin. Yes, so next portion of the presentation could go about understanding fundamentals of fluid level measurement. We would have a lot of information to cover. We'll try to shrink that. Justin has covered how to create the well file, setting up the equipment, the process of acquiring a fluid level shot. So when that's already done, you have the need to understand what's going on down the well. When you shoot a fluid level, basically what happens when you click on fire, you listen to noise going out, and from that point on, the next portion of the presentation is understanding how the acoustic wave works, how that travels down and up, and then interpreting that data. We will have examples covering different methods to determine the distance to liquid, looking at examples of how different type of wells respond depending on the changes that they have downhole. We will cover quite a few examples, hopefully by the end of the session. we'll be able to answer the questions we've been receiving on the chat. Again, your questions are welcome in the chat. We'll have a session at the end to address all of those questions. I've tried to answer directly some of them, but let's move forward. So as we know, the first session will go about understanding fluid level measurements. And on the slide, there is a rod pump well, but basically fluid level measurements can be applied to any type of well. And let me just use a rod pump well as an example, the most common artificial lift system. So on the slide, we have shown the wireless system. So all you need to shoot a fluid level using wireless equipment is just a computer with wireless base and a remote fire gas gun. In this case, it's a remote fire gas gun. We have also a 5,000 PSI gun. But basically, when you shoot a fluid level, what you're getting from that measurement is having a top of the liquid calculation. And we'll talk about how to get there. We will interpret the acoustic data, and this is a real example. We have an acoustic trace and a very simple liquid level kick. We will understand what that means later on. But on top of that, the software can also use the hardware and the connected to the wellhead to acquire more information. We just don't only acquire acoustic data, but we also collect pressure data. So there is a built-in pressure transducer in the wireless gun. There is also an external pressure transducer in the wired guns, as you may be most of you familiar with. And that pressure transducer will be collecting pressure data and how that pressure changes in time during the short time period that you collect the acoustic measurement. So in this example here, we have a regular 2-minute pressure buildup, and that information is critical if your well produces any gas. Distance to liquid calculation is one thing, but then understanding well potential will require you to understand how much pressure you have bottom hole. And in order to understand the pumping day pressure and the producing bottom hole pressure, it is really important to understand the composition of that column in the well. So we will use the fluid level information. We connect equipment on surface. Nothing is running the well, as you know. It's portable equipment connected there, send the pressure wave, understand where is the top of the liquid column in the annulus. And then based on additional information, which is tubing size, casing size, pump depth, perforation depth, we can also determine how much gas and liquid is present in the annulus. So with that, the software, with that information, tubing, casing, pump, perforations, the software will be able to calculate the liquid percentage in that column. And based on that liquid percentage, we'll be able to calculate pumping tape pressure, producing bottom hole pressure. Reducing bottom hole pressure is critical when you're trying to understand well potential. So one of the purpose of the measurement could be optimizing production. And in order to do so, we have to understand what is a drawdown from the formation. So with Echometer, we can calculate pumping tape pressure, flowing bottom hole pressure, but if the well has been down long enough, we can also calculate static pressure, which will be static bottom hole pressure, basically the reservoir pressure. So with this equipment at different points in time, we'll be able to determine a couple of pressures that will allow us to determine also well potential. So we'll put together a regular IPR curve, static pressure, flowing pressure, and the flow rate at this bottom hole pressure, and we'll have a good idea about our well potential. Compare that to the current flow rate, we have the production efficiency, and we'll have a good idea how to optimize the well production. So the good indicator, very simple to acquire, takes just a few minutes, very simple, quick, and very economic to perform measurements with Echometer equipment. We have people already connected from about 12 countries, and I'd like to quickly go there and show a list of countries we have right now here connected. At least I saw people from India, Ukraine, Egypt, Latvia, England, Brazil, Ecuador, Suriname, Colombia, Canada, and also, of course, from here, from the US, some people. So for many of you, you will see units in the software that are basically feet PSI, so we have length, velocity, pressure, units, but all that can be converted into metric system if that's what you use in your country. And I will show some of that later on. So thank you all for joining us from different places. Purpose of the measurement. So Echometer equipment, or Echometer technology as it is used in a wide variety of conditions, of wells, of even the purpose of measurement could be optimize your well, troubleshoot. If you have a producing well, an oil or gas well, even to water wells, if you have an injector well, even a gas storage well, you're not really producing, you're storing well, all those type of wells use Echometer equipment at some point, even abandoned well for regulatory fluid level measurements. So you can see pretty much Echometer being used anywhere you have oil or gas production. And one of the most common uses to follow up on the well and then do troubleshooting is fluid level measurements with production optimization purposes. Understanding well performance, we need to understand about bottom hole pressure. You can troubleshoot the well by acquiring data with Echometer equipment. If you have a failure, if you have a loss of production or reduction in production, you can go and understand what's going on in the well by using Echometer technology. It's widely used to understand about holes in tubing or tubing casing communication points, a gas lift valve passing. There are newer techniques, and we'll be covering this section in the last day, the day 3 of this series. So after tomorrow, we'll be talking about gas lift and special methods to identify holes in tubings or any other communication between tubing and casing. It's used for well integrity. That's widely used, especially offshore, where you do multiple fluid level shots between different casings. Obviously to troubleshoot wells, but also, as I mentioned before, for regulatory purposes. Abandoned wells, cemented wells, they still need to have some follow-up every year, every other year or so, and Echometer is also used to make sure that the levels in the well are where they're supposed to be. On drilling operations, anytime you are doing a drilling operation or a workover operation where you don't have returns, you have to monitor the mud level or water level in the well, the control fluid level, for pressure management purposes. So it's widely used in the drilling operations as well, where you have no returns, either because of a loss of circulation or you're drilling with special techniques like a nitrogen cap, where you need to understand where is the top of the mud, and Echometer helps with that. Even for surface facilities, is Echometer used when you're running a pig to clean the pipe, either to track the pig or the pig gets stuck somewhere. You can shoot what we call shoot a fluid level, but basically you're shooting a pressure wave down the pipe and understand where is the blockage. So understanding blockage detection and that purpose as well. So those are some of the purposes when you use a fluid level. So what happened when you connect the gas gun, click on fire shot if you have a remote fire gas gun, or you use manually operate the gun to release a pressure pulse down the well. So basically, what's happening there is the pressure pulse being released, and it will travel down through the space or area it has available. In this case, let's say you have a well with tubing, and you have some tubing cutters. So the pressure wave will be traveling down, and a small portion of the wave will be reflected every time it passes through a decrease or increase in cross-sectional area. So any change in diameter down the well will be creating echoes back to surface. The remaining energy will hit the liquid level, and the remaining energy will travel back to surface. Hopefully, we've been shooting fluid levels with enough energy so that energy will last long enough to go down, hit the fluid level, come back to surface, so we can read the echo in the gas gun microphone. So this is a short video that explains with wired equipment what happened in the acoustic trace. let me explain again what's going on here. So we have a video that's showing basically a wellhead has been cut so you can see inside the tubing and casing. That's the annulus area where the pressure wave is going to travel. So we apply some pressure in the chamber, and you may have different type of guns. This is a remote fire gas gun. So we're applying, in this case, CO2 pressure. It could be nitrogen. So we have those two type of gases to charge the gun with. We will charge the gun with the pressure exceeding the wellhead pressure, and Justin has explained the process before. The zero set has been performed, and you're ready to shoot a fluid level. So we send a signal from the well analyzer, in this case through the cable, activating the solenoid, releasing the gas pressure. We do the same in the wireless equipment by sending a signal to the gun, activating the solenoid again, and releasing the gas pressure to the well. Or you could be rotating a bar, pulling a trigger, any firing mechanism your gas gun may have, and that will allow the fluid level of, or the pressure to go off the gun. That will travel down the annulus, so that pressure wave will be moving in the area down the well, and any change in cross-sectional area will be reflecting a portion of the wave back to surface. So colors, if you have tubing in the well and shooting down the casing, colors will represent the change in diameter. So every time the pressure wave passes through a color, it will be reflecting at least a small portion of the wave back to surface. And that pressure wave will keep traveling down as long as it has enough energy and there is area to run down the well. So that will be happening until this pressure wave finds a total blockage. And what a total blockage is basically the top of the liquid level. There is no more room to travel, and that pressure pulse will be reflected off the top of the liquid and will be traveling back to surface. Now, this pressure wave will be traveling at a speed of sound in that gas condition or composition. And we call that speed the acoustic velocity. So every time we mention acoustic velocity, we're basically talking about how fast this pressure wave is traveling down and up the well. So we'll talk about that in feet per second most of the time, and you may have in other countries like meter per second, but we'll have that pressure wave traveling up to surface at a speed of sound in that environment that we call acoustic velocity. So what we have on surface, the microphone in the gas gun will be receiving the shallower color echoes first, and those are represented by these little yellow portions. And then last, there will be a bigger echo coming from hopefully the liquid level. So that information is sent via wire to the well analyzer, and that information will be interpreted by the well analyzer, and we can see that on the screen if you have wired equipment, or will be wireless transmitted if you have a wireless equipment. Basically, the resolution of the microphone is about the same. Data quality, well, you have a cable in between, and you may have better data quality if you have good communication through a wireless system, but basically it should be about the same if everything works fine. After collecting the fluid level data, the software will switch to acquire pressure data, and that's where you need to allow the software. We recommend usually around 2 minutes is enough time to collect pressure. The pressure buildup then will be used to calculate buttonhole pressure, understanding liquid percentage in the annulus and so on. So basically, that's how this works. And when we shoot a fluid level, let's start talking about the data we receive. So what happened when we shoot a fluid level? So we have something on the screen. It may look something similar to this, ignoring the colors. So we have a big kick that's coming off the fluid level shot. And that fluid level shot kick is represented on the screen. If the pulse type is selected correctly, you will have a down kick from the shot, and then another cross-sectional area in the well will be, in this case, a liquid level. You have a down kick from the liquid level. But remember, we're shooting a fluid level. The wave needs to travel down, hit the fluid level, and come back to surface. So we have actually a round trip travel time because we shoot from surface and we have a microphone expecting for that echo at surface. So every time we see on the plot is actually a round trip time to receive that echo from any anomaly or changes of cross-sectional area down the well. We have to interpret the acoustic pulse, because in this case we see a down kick, but it could also be an up kick. And we'll see some examples where you see down kicks and up kicks, and now trying to understand what that represents. Anytime you see a down kick, and this is just a test cap, if you have a microphone problem or you want to check how the microphone is responding, you can put a test cap, close the bleed valve, go to check the background noise, squeeze the bulb, and you should see a down kick. And down kicks are usually a representation from the fluid level. So every time you see a fluid level, it should be represented as a down kick. Most of the time is the biggest kick in the trace. Not always, but yes, most of the time the liquid level kick is the biggest kick on your acoustic trace on the screen. But sometimes you see up kicks, but up kicks will be usually coming from an enlargement in the well. So an increase in the cross-sectional area, like a perforation top. So basically, perforation top is a holding casing because there's nothing coming through that hole, or it's just gas. So basically, any increase in the cross-sectional area where the wave is traveling will be represented on the screen as an up kick. So most of the questions we receive on the support line or emails are related to interpreting the kicks, up kicks and down kicks, what they mean. So for us, it's really important to highlight that down kicks are reflected from decrease in the cross-sectional area, and the opposite, up kicks are coming from increases in cross-sectional area. We'll see some examples of that as well. This is a real example. Real data, fluid level shot. We see small echoes along the trace, and those are actually tubing color echoes. This is a fluid level shot down the casing where you have tubing in the well, and the color echoes, those changes in diameter in the cross-sectional area, are causing small echoes, and then you have a larger kick that is actually coming from the liquid level. So you see a down kick from the shot, a down kick from the liquid level. This should be a very simple liquid level to interpret. Now let's try to talk about different scenarios, because we have people from all over the world, and you shoot fluid levels down the casing, but a lot of people also shoot fluid level down the tubing. Some people don't even have a tubing in the well. It's just a gas flowing well or gas storage well, and they don't even have tubing. But let's see what would happen if you have changes in diameter down the well. So this example here, the top of this plot, we shoot a fluid level. There is a change in diameter. There is a decrease in this ID. So going down, you have a down kick from the shot. There is no changes in diameter until here. We have a decrease in the cross-sectional area. So the sum of the energy is reflected off this decrease in diameter. That's actually a down kick that reflects the area. The rest of the energy keeps traveling down. Energy travels down until it finds another change in diameter, which is actually a down kick from the liquid level. So we see a down kick from the liquid level as well. So it will be down kick from any decrease in cross-sectional area, also down kick from the shot. Different well. Now we're shooting down the annulus, where the tubing also has a change in diameter. There is a decrease in the tubing size, but for the annulus area, this decrease in tubing size represents an increase in the annulus area. So when you shoot a fluid level down the casing, what you see is a down kick from the shot. Then you see an decrease in the tubing size, meaning an increase in the annulus. So the cross-sectional area increases, and you see an up kick right there due to the increase in the cross-sectional area. So a portion of the wave is reflected with, literally would be an inverted polarity, but basically it flips the trace or the polarity of the wave, and the rest of the energy keeps traveling down until it finds another change in diameter. It goes from tubing, casing, annulus to only casing. When that happens, then a portion of the wave is reflected due to the increase, looking as an up kick. The remaining of the energy keeps traveling down until you find the liquid level, being the liquid level always a down kick. So you have this type of wells where you have multiple changes in diameter. You normally have to shoot with a good amount of energy so that the reflected energy, still you have some remaining energy to get to the fluid level and come back to surface. And we'll see some examples of that as well. This is real data. So quick example, we have kick sizes that depend on the change of diameter. So down the casing, if you have a tubing anchor, many wells have tubing anchors, pumping wells, that tubing anchor or partial restriction in the annulus area will be reflected as a down kick. Then you have a liquid level kick. If there is enough distance from the anchor to the liquid level, when the wave is traveling back to surface, that wave will pass through the anchor, which represents again a decrease in the cross-sectional area, giving you a down kick. But most of the time, that tubing anchor is very close to the pump. So this example here represents that there is a down kick, that small down kick here, and you can shoot again, and you should shoot at least twice, shoot 2 fluid levels, and then you confirm that that down kick is every time you shoot a fluid level, you receive a small down kick before the liquid level kick. So that's usually a representation of a tubing anchor. You should confirm this information with the well information. So you pull the well file, make sure that you have a tubing anchor above the pump, and that's what it represents. And then you have a liquid level kick. So that's a small kick from the tubing anchor, small kick from the liquid level. Another real data example. If you have a liner top, so you have a casing and a casing line, there's a decrease in the cross-sectional area down the annulus. When that happens, you have a down kick top to bottom, a down kick because there is a decrease in the annulus area when you enter the liner. So that's a down kick representation. Hit the fluid level, that's a down kick from the liquid level. And coming back to surface, the liner top now represents an increase in the cross-sectional area. When you leave the liner and enter the casing, that's an increase. So increases are represented as up kicks. Real data example, we see a liquid level trace, down kick from the liner top, even a bigger kick from the liquid level, and at the same time difference, we will have a liner repeat when that pressure pulse is coming from the liquid level back to surface to the liner top. Repeat. Echometer has available currently 6 different type of guns. Some of theirs are lower pressure, higher pressure, wired, wireless guns. So there's a variety of guns that you could be using depending on your well type or wellhead pressure. Even some countries have a really strict safety requirements, and some of the equipment must be intrinsically certified, class 1, division 1, and we have options for that as well. On the screen, you have low pressure guns. This is an oldest type of gun, the compact gas gun that is used for explosion and implosion shots. We have a wired remote fire gas gun. We have this equivalent version, wireless. That's a wireless remote fire gas gun, 1500 PSI. Then if your wellhead pressure is higher, usually gas wells, gas lift wells, gas storage wells, some high pressure wells will require 5,000 PSI working pressure guns. So there will be a limit of working pressure of 5,000 PSI. Again, it accommodates for most of gas lift wells, plunger wells, gas lift plunger assisted or gapple wells. Basically higher than 1,000 PSI, above 600-700 PSI. Usually users tend to move to the higher level gun, being the 5,000 PSI wired. We have a wireless version as well. So we have 2 wireless guns. And if your well has really high pressure, meaning the wellhead pressure, we're not talking about bottom hole pressure. This is wellhead pressure. The gun will be exposed to pressure at surface. If you have a surface pressure above 5,000 PSI, then we have an option for a 15,000 PSI gas gun. As you can imagine, not many wells have that such high pressure. So, but we have an option for that as well. That's only wired. So different type of guns are able to perform different type of pulses. So what this means, basically you can do 2 type of pulse, or you can generate the fluid level shot in 2 different ways. You can do explosion or implosion pulses. What explosion means, basically we are charging the gas gun chamber with more pressure than the one in the well. So we're increasing or charging the gun with exceeding pressure than the wellhead pressure. This example here, wellhead pressure is 100 PSI. When then to do an explosion shot, you'll require to charge the gun above 100 PSI. Common question is, how much pressure should I put in my gun? Is 200 PSI. Some people shoot regular with 300 PSI. Some people requires a lot more. Some people shallow, low pressure wells just put 100 pounds. What's important is you have more pressure in the gun than in the wellhead. And we recommend to start with 150 or 200 PSI above the casing head pressure. Whatever that casing head pressure is, we recommend you to start with 150 to 200 PSI above that pressure. So this example here, the difference of pressure, 300 versus 100, is 200 PSI. It doesn't mean that 200 psi, it is the amount of pressure that the differential pressure that you need every time. It will depend on the well noise, how noisy is your well, how deep is the fluid level. And you can imagine a low liquid level, so deep liquid level, let's say, in a deep well where you have lots of noise, you will require a lot more differential pressure than if you're shooting a fluid level in a shallow, quiet well. Let's say you have a T8 well, no pressure, just 50 psi on surface, versus a 10,000 feet deep well, lots of noise, then your pressure requirement in the gun will be much higher. So differential pressure depends on what the well needs. Start with 200 psi, go from there, see what you see. Can you detect the liquid level kick? Maybe yes. Can you count colors? So do you have any other method to determine distance to liquid? We'll be talking about these topics in the next couple of hours. So explosion pulse, pros and cons. You have to bring to the well an external gas source. So you have to bring a cylinder with gas. We recommend to use CO2 or nitrogen, depending on your wellhead pressure, your ambient temperature in that zone. You may be using CO2 or nitrogen. You may prefer. Availability is another factor that plays in there. But either CO2 or nitrogen, those are clean gas, inert gas that will not contribute with combustion. So those are our two recommendations. We can sell equipment with either type of gas cylinder. So you can tell us what type of cylinder you need for your operation, CO2 or nitrogen, and we can provide that as well. This remote fire gas gun is only able to perform explosion shots. So if you're using a remote fire gas gun, you must charge the gun every time above the wellhead pressure, exceeding the wellhead pressure. There will be a gas chamber at 12 cubic inches above that, where you compress the gas at a pressure exceeding the wellhead pressure. The other type of pulse that is possible to perform is an implosion shot. It's basically the opposite. You always need a differential pressure at the wellhead to create the shot, and that's now having less pressure in the gun compared to the wellhead pressure. So for this type of shots, you will require the well have some pressure in it. So you require the well is live, so you have some pressure, and let's say at least above 200 psi if it's a deeper well, maybe a little less if it's a shallow well, but you need some energy from the well so you can take the pressure of the well into the gun so you can quickly generate the differential pressure, and that's basically the shot. That's a pressure pulse now with the inverted polarity. It's a refraction pulse, but you're still sending a pulse down the well. It's a negative pressure pulse. Pros and cons of this, well, a good thing is you don't need to bring gas cylinder to the well because you already have energy in the well. You don't need to bring more energy. The downside of this implosion shot is you are bringing, most of the time, not only gas from the well. If you think about it, when you open a casing valve or a tubing valve, it's not just coming clean gas out of the well. There is some debris, there is some dirt coming from the well, and that dirt will go to your gun, which will normally mean you will require more maintenance in your gun as you're using energy from the well and you're pushing that into the gun, and it's not just gas. It will be more debris as well coming to the gun. So you'll require more maintenance. You will save gas. There are always pros and cons in any situation. Depending on the well production or the well pressure, you may be able to do an implosion pulse if you had the right type of gun. So which guns can do implosion shots? One of those is the compact gas gun. Remember that working pressure for this gun is 1500 psi. So it's 1500 psi. And I will have to convert those into bars or kPAs for other people. I'm sorry for that. I'm not that good in all those pressure conversions in my head. So 1500 psi, you do your math and convert that into your unit, please. So compact gas gun can do both explosion and implosion shots. We have an 8 cubic, I think it's a 7 or 8 cubic inch chamber where we can compress gas and do explosion shots, or we can let the pressure come from the well into the chamber to do implosion shots. There is a gas valve, there's an O-ring down here, cylinder chamber, and that will be a common part for replacement when you're doing a gun maintenance. Another gun that can do both explosion and implosion is the 5000 psi gas gun. That gun is actually, we have both versions. This is the wireless version of it, but we also have a wired 5,000 PSI gas gun. It's very simple. It's the simplest gun that we have to operate. Just rotating this valve 180 degrees will allow you to create the shot. And this can do, again, explosion if you charge the gun with normally nitrogen. Could be CO2 as well. Then you can do explosion shot, or if you have wellhead pressure, by rotating the valve, having no pressure in the chamber, you can do an implosion shot as well. So both ways, explosion, implosion, 5,000 PSI gas gun, normally used for higher pressure wellhead. Now, regardless the type of pulse you perform, what's important is you have to tell the software what type of pulse you're doing at surface. So if you do explosion shots, that will actually be the pulse type by default in the software, so you don't have to change it. But if you're using a compact gas gun or a 5K gas gun, you'll be doing an implosion shot. You have to tell the software you could do an implosion shot with those guns. This example here shows that the interpretation of the data is not going to change. So this is an explosion shot, and this is kind of noisy, but let's look at the reflections here. So we have an up kick, down, up. And if you look at that, now it's shooting the flue level as an implosion shot. As long as you tell the software the right pulse type, the data interpretation will be the same. You still have an up, down, up kick, with some difference in the amplitude based on the pressure you're using on the shots. But basically, you will be able to interpret the shots in the same way every time. When you're shooting fluid levels, actually, you can use the acoustic data to answer many questions in your well. And one of the common questions is, where is the liquid? Basically, people shoot a fluid level to understand where is the fluid level, but you can understand a lot more than that. The most primitive equipment that we have does this. So we can, with good level of certainty, determine the distance to liquid, but also you can, on top of the liquid level distance, you can determine a lot more information that's valuable for your well analysis. So is there any liquid above the pump or the end of tubing? If you don't have any pump in the well, you'll be able to determine how much pump submergency or liquid above the end of tubing you have. Is there any gas flowing up the annulus? Because more than just the liquid level, we're also measuring pressure and using that information to determine the gas flow rate. Disclaimer is we are not pretending to replace a gas meter, but we use the pressure buildup to determine the gas flow rate at that point in time, in that couple of minutes, to understand about liquid composition in the annulus, which will allow us to determine bottom hole pressure. If there is gas flowing in the annulus, at what rate? Then use that information to understand what is the percentage of liquid in the annulus column or in the well liquid column. Use that information to understand bottom hole pressure and what is the system efficiency. So we can determine production efficiency in the well by understanding well pressure and production, and use that information to understand well potential. So we have to input the well production. So you have to input water production or workout. You have to put how many barrels of water, how many barrels or cubic meters if you are in another country, of oil or condensate, and how much gas, and the well would calculate potential for you using we have a couple of methods in software. We have the IPR method, which is the most common one when you have gas production, and we have the IP method. So it's all based on production parameters, well production, bottom hole pressure. All those questions can be answered by looking at the report. So when you click on the software, you click on report, you will have access to, so this slide is actually meters. So you'll be able to understand where is the liquid level, how much pump submergency you have for liquid above the tubing. You can understand what is the annulus gas flow rate. Use that to calculate the liquid percentage in that column in the well. Use the liquid column to understand gas free above the pump, but also when you calculate bottom hole pressure, and you can see here, producing bottom hole pressure, the user has input a static bottom hole pressure, or this comes from a previous static fluid level shot. And with this information, the software will be able to calculate well potential. So this well is pretty much pumped off. We don't have much pump submergency, maybe a couple of joints, And if you try to increase production, really, you don't have much more room to go. So you're producing all the oil you can. You may produce a little bit more of water, a little bit more of gas, but basically you're pumping off, you're close to the maximum production rate in this well. Actually, it's 97%. So those kind of answers, you can find them. If you provide enough information, the software will be able to tell you that this well is producing at maximum rate. There is not much more production you can get from here. Why is it important to allow the well to collect pressure data? Well, that's critical if your well produces gas. And let me use this slide to explain that. When you shoot a fluid level, it's not enough information just to know the top of the fluid, because based on your well configuration, you may say, okay, I have the fluid level, and from that fluid level top to the pump, I have 5,000 feet of liquid. That's equivalent to 1,600 meters or so, but that's a lot of pump submergency. So say, I have a lot of room to improve this well. I have to, if it's a rod pump well, you have to increase the speed or change the stroke length or increase the plunger size in the next workover. If it's a PCP, you have to increase the RPM. If it's an ESP, you have to increase the hertz, because you, according to this, you have a lot of production to take, because at such a high producing bottle pressure, you have to increase the drawdown by improving production, pushing the fluid level down, and having less drawdown, or actually a bigger drawdown. Now, that may be totally false if you have ignored the gas production in the well. That's why it's critical when you're shooting a fluid level, allow the software some time to collect pressure data, so that you will have now the ability to calculate the liquid gas percentage in that annulus. With that information now, there's supposed to be 5,000 feet pump submergency column. Now, when you account for the gas bubbles flowing through the annulus, you will now have the equivalent. Maybe this well is only 24% liquid, 76% gas. So your 5,000 feet of liquid, actually, when you allow the software to calculate gas production or gas flow rate and liquid percentage in the annulus, the software will calculate a gas-free equivalent of 1,200 feet. What this means? Well, if you could, let's say, would take a picture of the well and allow these gas bubbles to separate, the liquid amount actually drops to 1,200 feet of pump submergency. And that's what the software will effectively use to calculate pump intake pressure and producing bottle hole pressure. So now, by allowing casing pressure buildup, you're letting the software to calculate a more realistic producing bottle hole pressure, which will be a much better value to calculate well potential. That's the importance of casing pressure buildup and allowing the software to collect some pressure data. Let's cover a couple of slides with equipment. So we have wired equipment, and today we'll be just talking about gas guns, and you may be familiar with the well analyzer. So this is the main component. You will have a well analyzer and a computer, and run cables to a wireless gun. It may be a compact gas gun, remote fire like this one, a 5,000 PSI, or even a 15,000 PSI if you're in the wired world. Bottom here, we have some dynamometers, but we'll talk about that tomorrow. So you'll expect to see you in tomorrow's sessions for fluid level, for dynamometer. And then last day, again, we'll be covering gas lift, gas wells, plunger lift, and techniques to identify communication points. So we have a good number of topics for day 3. How we connect the sensors of the well. Well, today we're talking about shooting fluid level. So we're connecting, this is a pumping well, so we're connected to the casing side. It could be a gas flowing well or a natural flowing well where we shoot the fluid level down the tubing, or maybe a gas lift well where we can shoot fluid levels down tubing and casing, or a plunger lift. So depending on the well type and the purpose of your measurement, you may be connecting the gas gun in different places, but basically you have a fluid level gun, and if it's wired, some pressure transducer and cables running to the well analyzer. We'll talk about dynamometer sensors installation tomorrow. Or if you're, probably some of you are not familiar with wireless equipment, you will have a gas gun, maybe a 5,000 PSI or remote fire. You have a wireless base and a computer. So this is a must. So you need a computer with a base to talk to any of the sensors that you're connecting to well. So fluid levels, we're stuck to this. We're talking about these 2 sensors up here. tomorrow we'll talk some more about dynamometer sensors. Connecting the sensor to the well, same thing. We have a gas gun connected to the case inside, and we may simultaneously acquire more data, but again, that's a topic for tomorrow. So you have a wireless base connected to the computer where we can simultaneously collect fluid level and dynamometer data.
Somebody's in trouble bringing
So
HR.
basically, we have a technology that can be used technically in any type of well. It doesn't matter if it's a pumping well, a gas lift, an injection well, gas storage well. The only point where I don't think we can shoot a fluid level is when a hydraulic pump, like a jet pump well, is flowing. So you have injecting in the annulus, producing in the tubings, it's full of liquid. But aside that, you can do a fall-off test on that well. You can, when it's static and the fluid level drops, you can monitor the fluid level dropping, understand where the fluid level is at in static conditions. So there's always a measurement that can be performed in a well using the Echometer technology. And with that, we'll be now talking about some acoustic measurement analysis. So in this case, when you shoot a fluid level, we're going to analyze some of the data to understand where is that liquid level top. So when you shoot a fluid level, and I'll be switching while during this presentation between the presentation and the software. So we'll start kind of switching between presentation and the software. And let me use this as the first example. So first thing, when you're analyzing the fluid level, and for the ones who don't know TAM, this is TAM software. For those TWM user, which is an older Echometer software, for us it's becoming a legacy software basically. Brief comment about TWM. This is an older Echometer software. We are not, and we will not work anymore in TWM. And this is TWM for the ones that maybe newer users only know TAM. And TWM, this is what it is. It's not even, you cannot even do a full screen. It's about 27 years old software. We stopped any development on TWM over 10 years ago. So 2012 was the last time that an improvement was done to TWM. And we're not planning to continue doing any improvement to TWM. So since 10 years, we've been working on TAM, and we continue developing TAM. We currently have other modules. You can acquire data. Nowadays, you can go to the website, and Justin showed you how to go to the website, to the software section, and download TAM 1.8.56, which is the released version from last year. And we're working on 1.9 with several improvements. Day 3, we will show some of 1.9 and this dual shot technique as well. But again, all the data you have in TWM, it can be transferred to TAM, but we're no longer working on developing TWM. So if you're a TWM user, depending on how old is your well analyzer, the hardware, that box, it may already have a TAM license if it was purchased not more than 7 years ago. So since January 1st, 2016, all well analyzer has been sold with a TAM license with it. If it's an older well analyzer, even before 2012, TAM didn't even exist then, so it doesn't have a TAM license, but you can upgrade that well analyzer by purchasing a TAM license. So you don't have to buy a new well analyzer, but you can purchase a TAM license to be installed in that hardware, in that well analyzer, not in your computer, not the software, because the software is free. Anybody having a Windows computer can go to the website, download the installer, install TAM software. We sent a link in the invitation where you can click on, takes you to the website where you can download TAM software. Running in your computer, we send you a file with these examples that you can download in your computer and practice with them. So this is a free software, free of use for anyone. But if you have an older well analyzer, you will require to purchase a license to just no longer work with TWM and start with TAM. You wouldn't lose your data. Again, all the data can be transferred from TWM into TAM. Now, we'll be talking about TAM for the next 3 days. So this screen here is the liquid level screen. Much better navigation, much simpler to use. And we'll be talking about today fluid level. So this is a liquid level module. This well, we have multiple liquid level kicks. So this is the real data that you receive when you shoot a fluid level. And depending on the well depth, you may have a long acoustic trace. It doesn't mean that you need to interpret all the data. We can focus on the important part. We understand the well is producing, and there must be liquid level above the pump intake. One of the benefits of TAM is it can overlay the wellbore schematic. And so you can see in the background, you have a wellbore schematic overlaid. So it means the pump is down here. There's a tubing anchor in the well, but the liquid level is up here. So let's talk about interpreting that liquid level data with fluid level measurement. So we have a down kick from something in the well. So something in the well is creating a big down kick. So if we look at the wellbore schematic, what could be causing a down kick? Well, first, we need to remember down kicks are caused by decreases in cross-sectional area. Like the liquid level is a total decrease, it's a total blockage in the annulus. So we're expecting to see down kicks from decreasing cross-sectional area. By looking at the wellbore schematic, we observe that there is no tubing change in diameter. And I'm going to just come here. I'll click on edit. And I'm looking at the detail view, not the quick view, because in the quick view, we don't have much details. Going here and go to the mechanical wellbore, there's only one tubing size. And if you have a tubing change in diameter, you will have a different row. So, and this is basically translating your well file information into the software. And there is only one tubing size. There is only one casing size, so there is no casing liner. With this, you may have all other components in the system that you can highlight here or input here in the hardware section, but there is nothing at a shallow depth of the well, less than 2,000 feet, that could be causing a down kick. So that must be the liquid level, and it has the characteristic of a liquid level kick. So let's talk about that. You can increase or decrease the scale. There is a subplot up here where you can manipulate that to show a section or portion of the acoustic trace. There are other plot controls that you can select a region if you want to zoom in. Go back to the previous view. So there is quite a few visualizations features in the software. So we have a big down kick, and there's nothing that's supposed to create that but the liquid level. So I'm expecting to see a high liquid level. So what this means is the liquid level line, this LL line, actually the time to that is RTTT, that's round trip travel time, that appear at 2.5 seconds. So with that, we have a down kick at 2.5 seconds, that's 2.55. And the energy, so when we shot a fluid level, the fluid level wave or the pressure wave traveled down, hit the top of the liquid and came back to surface in 2.55 seconds. Now, the energy that hit the microphone is this much. What will happen to that energy? Well, it doesn't disappear. It travels down the well one more time, hits a fluid level and come back to surface. So we see a repeat of the liquid level. And where do we see the repeat? 2.55 seconds after. So it doubles time. So we can plot using annotation, and there is a depth reference line. We will cover that as well later. And I'm starting to use some of the features. And actually at they're right there, 2.51 is double of this time. We have a repeat. So it is a down kick exactly at double time of the liquid level. And then we see another kick. Well, that's again 2.55 seconds after, and 2.55 seconds after, and so on. So we have multiple liquid level repeats. What that means? Well, it means when we shot a fluid level, it had enough energy and recording time to see multiple repeats of that fluid level echo. So for our interpretation, these kicks are just representing a confirmation that this is the liquid level repeat 1, repeat 2, repeat 3, and if we keep going, we may see other repeats as well. That little kick there is another repeat, but we don't need to focus on that. We need to understand what is the distance from surface to the liquid level. So our analysis will be focused on this area, but these have the characteristic of a simple liquid level shot. It's a down kick, the rest are down kicks. They have smaller and smaller amplitude, so the size is decreasing because the energy is dissipating, and they are at the same time difference. So these three things are compliant. So we check the box. It's all down kicks, same time difference, and the amplitude is decreasing. So smaller and smaller and smaller until we can't hear it anymore. So we are confirming the liquid level here is at 2.55 seconds. Now, do we say that? Well, we could move the liquid level line as you see I'm doing it, or the software by default will select the liquid level for you. Even if you're playing with that, you can always ask the software, where do you think is the fluid level? The software will do an automatic liquid level selection. And I can go back there by going to fine tune and go to liquid level. And you make this a full screen or not. Well, I think we need a full screen, but by clicking on reset, the software will put the liquid level line where it thinks is the liquid level. So it's your job to confirm that the software is doing this correct. So the software selected the liquid level at 2.55. And actually, I agree with the software this time. And yes, most of the time, the software will be correct. If having a casing liner or a change in diameter above the liquid level is common in your operation, the software may be wrong. Or if the fluid level kick is actually very shallow, below 1 second, the software may be wrong and will probably pick the second or the third liquid level kick, as the software is not programmed to look for such a shallow liquid level. So yeah, the software will automatically select the liquid level, but it is your job to select the liquid level correctly. And we'll see some examples of how to select the liquid level. But in this case, the liquid level is very simple. Software did an automatic selection. And yes, most of the time the software will be right. Now we know the time to the liquid level. So we know the liquid level is at 2.5 seconds. So if I'm a service provider or I'm out in the field and I call you back and say, hey, your liquid level is 2.5 seconds from surface, would that information be enough for you? Say, no, I need to know the distance to the liquid level. So how do we convert in this plot 2.55 seconds into distance? And the distance in this case is 1537 feet. We can change that to meter just by clicking on the unit. It's really simple to switch feet to feet or meters. And we have multiple users. I'm going to quickly go to utilities, preferences, and these are the units. So we have all field units. You can do a international or metric system, or you can have a custom unit where you can pick which units to change. So I will keep it on all field for my remaining of the presentation, but you're welcome to change that to whatever you want, or you can do it from the unit itself. So I can swap this to, instead of feet per second, meter per second. So you'll maybe more familiar with some of those numbers. Again, I'm just gonna bring it back to feet so I can keep talking about it. Recapping, liquid level selection. The first step when you are analyzing a liquid level is make sure the software has picked the liquid level kit correctly. Yeah, the software did that. I'm happy with it. I agree with the software. What's next? Well, next is calculating distance to liquid. How do we calculate distance to liquid? We just have, at this point, by moving the liquid level line or by selecting the liquid level kick, we have a 2.55 seconds time. Somehow, the software converted 2.55 into distance. How the software did that? By knowing the speed. How fast was that wave traveling? Well, the software has calculated 1185 feet per second. So the discussion of the next portion of the presentation talks about how the software calculates the acoustic velocity. So AV stands for acoustic velocity. So we have time to the liquid level. Now we're going to focus on calculating acoustic velocity. So this is a snip of a fluid level report. And there is a liquid level kick in this example that is about 11.5 seconds. You see a down kick, a big kick at 11.5 seconds, which represents the time to the liquid level. Somehow the software understands that close to 11.5 seconds represent almost 6,000 feet of fluid level depth. So far, our challenge is to convert that round trip travel time into distance. So if we have time, we have to convert that time into depth. All we need to know to convert time into depth is speed, is the acoustic velocity. So we can determine acoustic velocity by using different things based on the acoustic reflections. What is that response, the acoustic response we have from the well? So one option, and this is actually the default by the software, we can use color reflections. If you have colors visible in the well, assuming you're shooting, for example, a casing shot and you have tubing in the well, and you can use the tubing colors. You may not have that, but you may see another kicks different than the liquid level, and you can use a known downhole change in cross-section area. So if there is a change in diameter above the liquid level, you can use that change in diameter to calculate the velocity. And again, with the velocity and time, you can determine the depth to the liquid level. So you can use colors, you can use a change in diameter, or if you don't have any of that, the last options we give you is using the gas gravity or gas composition. And we'll talk about that. How do we cover this in the software? Well, we give you these three options in the software. We use a method one that's using a color count. Using a change in diameter, we call that a downhole marker. So if you have any kick in the well that you know the depth, that's what we call a downhole marker. You can use that as a reference point to calculate the velocity. And again, velocity and time to the liquid, easy to calculate the distance to liquid. Or we have a third option that we just call acoustic velocity, and you have a couple of options inside that, and that's using the gas composition or the gas gravity, or even manually input the gas, the acoustic velocity. And we'll talk about these three methods in the next slides. So let's start with method one. Color count is actually the default method in the software. So the software, every time you shoot a fluid level, if you don't change anything, the software will attempt to count colors. Even if you don't have any, the software doesn't know that. The software will look at the acoustic trace looking for colors. Most of the time, when you have colors to count, there is no actions required by the user. And it's kind of alarming, but we have some phone calls, people that have been shooting fluid levels for a while and say, I've never done anything. I just connect the equipment, shoot the fluid level, and print the report. And good news is the software most of the time will do the work for you. The software will pick the liquid level for you. The software will count the colors for you. And the software will give you a very good distance to liquid level calculation by just automatically calculating that without any user intervention. Some wells, you may have to intervene, where the liquid level is not picked properly, where the color count is poor, and you may need to shoot with more pressure. And we will talk about those topics here as well. So the user may have to manually change or adjust the color count based on where is the C line located. And what is that C line? Well, the C line indicates the last color counted in the trace. So remember, the software will be trying to see colors in the acoustic trace, and after some point, the software may no longer see any color to the liquid level. So depending on where is the C line, and I'll talk about this in a second, you may need to take some actions to improve the quality of that shot. Something that is really important is you enter the average joint length. What is that? Well, you're counting colors. Color to colors is one tubing joint or one casing joint. And if you want to use that, let's say you have, let me do a random number, 100 colors or 100 joints to the liquid level. Well, you need to know how long is each joint to calculate distance to liquid. So let's say a joint is 9.6 meters for the ones that use meters. Well, 9.6 meters times 100 joints, that's 960, I hope I'm okay, joint, 160 meters to the liquid level. If your joint is 32 feet long, well, times 100, that's 3,200 feet to the liquid level. The software needs to know how long is each joint, and that will be entered with the average joint length. That's really important if you want to have an accurate calculation to the liquid level by using the color count method. Now, let's look at some real data. The acoustic trace will be represented on the screen, and we have the time to the liquid level 5.329. That's coming from the average well example. Every time you install the TAM software, there is an example folder with the number of wells. One of those wells is the example wells, and you can always pull and look at that, and has this acoustic liquid level reflection. So the software will select the liquid level and determine distance, time to the liquid, and with some information, we'll calculate the average joint length, and we'll go there for a second. So we have also a C line. If you see that little red line, hopefully that will be close to the dashed liquid level line. And what is that C line telling you? Which, well, the software was able to count colors all the way down almost to the liquid level. So those are good news. The software was able to identify colors down to the liquid level. That C line, that's what it means. And you can apply filtering if the data is too noisy, and we'll see an example of applying low pass filter. But basically, let's compare a low quality fluid level shot to a good quality fluid level shot. So we said, as the color line is close to the liquid level line, then the software was able to identify colors almost all the way down. So the software see colors all the way down, almost. But some shots will look like this, where the C line is far from the liquid level line. So if the time to the liquid level is the 100% of your distance, the C line is about what, 45% of the distance to the liquid level. So this is even less than 60%. We recommend to have a color count that is 70 or maybe 80% of the total number of colors. So this lower plot here is what we consider a poor color count. You can see other things in the well, but the color count was terrible in this one. So you will have to take actions on this shot to improve the quality of this data. Something important when you're analyzing fluid level shots using the color count is the average joint length. And this slide shows different sections in the software where you can input the same value. So the average joint length can be input by just clicking on the tubing on that plot right here. So if I click here in the tubing, that's the tubing length. Or you can click on edit and go to the quick view. That will be on the tubing table, or on the detail view on the second tab, mechanical wellbore, you have that portion there. So let me do it here. If you go to edit and you're in the quick view, that'll be right here. Or we highly recommend you to stay in the detail view. You have an opportunity to put much more details, and the mechanical wellbore is right there. It's really important. The software has a default at 31.7. So every time you see 31.7, you have to fix the value. You have to find the tubing information and input the best average possible so that your calculations are more accurate. Okay, let's look at some software examples now. Let me go to the software again. And let's look at how the software came calculated 1185 feet per second. Well, we have a method one, so the software is counting colors, and we can see the color line very close to the liquid level. And let me expand this some more. So you see all these lines, the little kicks, those are colors. So the software has been counting those colors and was able to identify colors almost all the way to the liquid level. If you want to look at closer what the software did, you can click on color count. By clicking on color count, it will open this window here. And this is basically a 1 second wide screen. It actually goes from 0.5 seconds to 1.5 seconds this time. And this is automatically selected by the software. You can manually change the area, but automatic selection most of the time works okay. And you can see those multiple down kicks in the tray. So the software is doing a good job. You have different options to filter the data. And maybe the high band pass filter works better on this one. You can see those big kicks. So the software is doing a good job selecting the colors. You want to see how many colors the well counted. Well, the software is not only looking at 1 second. The software is looking at all the acoustic trays. You can click on all colors, and that will open an all colors window. And what the software will do, it will split the time to the liquid level in 2 second pieces. So this is the shot time, 1 second, 2 seconds. then this will be 3 and 4, but the liquid level is only at 2.5 seconds. So this is the time to the liquid level. Any vertical line here represents a color counted. So we have a number of colors counted. In this case, we have 40 joints counted out of 46. So if we calculate that, we have 40 out of 46. So we have 86% plus 86% of the colors counted. This is an excellent color count. And yes, I'm happy with that. I agree with that. I have already checked my tubing average joint length. And so I have everything I need. I'm pretty sure because we have physical evidence. The software is counting colors. I'm telling you, I was able to count this many colors, and I was able to calculate the acoustic velocity based on how many colors the software goes through. And if you see, quick comment here, there is no colors counted at the very beginning after the shot because there is too much noise. When the shot goes off, the software kind of goes mute, or in this case, deaf, because there is so much noise that it can identify what's actually a noise from the shot and where the echoes coming from the very first few colors. Like a quarter of a second after the shot, the software started counting colors, and you could see the acoustic wave is traveling and passing through over 18 joints per second as an average, and can calculate as an average the acoustic pulse is traveling through 18.15 joints. Well, we know how much is each joint, and the software used that information to calculate the acoustic velocity. So we have an 1183 feet per second acoustic velocity calculation, and that is what's shown in the software. That'll also be in the report, but we'll talk about the report later. So now we have time to the liquid from the beginning by selecting the liquid level properly. And now, by using a color count, we have an average acoustic velocity. With those two values, now the software is able to calculate distance to liquid. So 1538 comes from a correct liquid level selection and an average joint length coming from a good color count and a corrected average joint length. So this is all good, and we're happy with the fluid level information that we received from this well. We can see another example. I'm going to pick well, and let's go to color count 2. So let's see another fluid level shot. We're just now talking about distance to liquid level. Later on, we'll come back and talk about the pressure buildup information. But this is another fairly simple liquid level shot. Will be some other that are a little bit more complicated, but same thing. Down kick, 3.6. So 3.6 seconds after, we could see a repeat at 7.12, and that's where we are. 7.2, sorry. So 7.2, we have a repeat. And then probably at 10.8 seconds or close to that, we have another repeat. So every 3.6 seconds, we have a liquid level repeat. So that's a liquid level. We need to count colors. And one more time, the C line, the color count line is close to the liquid level. So that's promising. The software has selected correctly the liquid level. The software has counted colors all the way down to the liquid level. That's good information. We look at the information, 31.7. So whomever created this well file, he missed that data point. You need to go back and see that information and see if you can fix this, because you will have some error associated to this lack of information. Why is that? Well, the software has identified that you have 69 joints. If you are 1 feet off, so if this 31.7 is actually 30.7, your liquid level will be off by 69 foot because you have about 1 foot of error per joint. That's why it's important for you to fix that. The deeper the well, the most important the value is. But we have, again, 63 out of 69. So we have over 90% of the colors counted here. That's excellent color count. And if we look at the acoustic trace, you can see it's a little bit more noisier. You can see how kind of dark it is. And normally, this is a condition in ESP wells. Because remember, every change in cross-sectional area will create small echoes to surface. And you have the cable clamps between joints that is also creating echoes in the well. Okay, so normally when you see noisier acoustic traces, that's very common in ESP wells, again, for the color clamps. But aside that, the color count was excellent. I know we'll have a small deviation if the average John length is not quite 31.7, and so there's a good chance that that's not correct for your well. But using the time to the liquid level and an acoustic velocity, again, calculated based on that, and we can go to this method one more time and go to all colors if you want, and you see 19.1, 1923 average. How the speed is going is 19.16. Using 31.7, we can come up with 12.15, and that's what the software is using to calculate 22.13 to distance to the liquid. That's very common here. You see multiple kicks in between, but distance to liquid, very accurate. And we have now a pump submergency and a gas-free equivalent pump. And I will come back to this in a second. So let's go to quickly check another one before we go to the break. A very simple one. This is a more clean fluid level shot. You see color echoes all the way down. Very low pressure increase, so this well produces almost no gas. Calculation is here, what, a couple of MCF per day? Yes. And we have the same characteristic. Down kicks, repeating, actually repeats all the way to the end of the recording. We don't need all that many. We see is at the same time interval is down kicks, all of them, and it's decreasing in size. So yeah, that's very simple, liquid level reflection. Going to color count, we can look a little bit up the report. We have pressure buildup. We have 90% of liquid content or liquid percentage in the annulus. So the software has calculated a distance to liquid of 2,000 feet to the liquid level, having a pump submergence 5,500 feet, but gas-free, only 90% of that column is liquid. So we have a gas-free liquid percentage of 5901. The software has no values in the current or potential. Well, the user didn't input any production data. We can see no production data input. So that's a piece of information you need to input if you want to calculate well potential. The software doesn't have enough information to calculate that. The software doesn't have a static bottom hole pressure either. So there is some information missing that now without that, the software is unable to calculate well potential. But we can have distance to liquid, we can have pump intake pressure and producing bottom hole pressure. That's still very valuable information. We're a couple of minutes away from the break, so let me go back to our first example. We see here a good pressure buildup, and this is a linear pressure buildup. That's what you're expecting to see. It doesn't have to go building up, but it has to be linear. So most of the pressure points must remain on the same line. So we look at this trace, this is very linear too. If we look at other shots here, this is a very good pressure buildup. You see, most of the points are right on the line. And that's ideal. That's what you're expecting. If you don't have that, you have to allow the software more time. Why is this important? Well, I told you we use the pressure buildup to calculate bottom hole pressure. So we have here 759, close to 760 psi to the pump intake. So let me keep this on the side. And that will be, let's say you didn't record for quite 2 minutes, but you stopped sometime before. If you stop sometime before, the software will calculate very close pump submergency or producing bottom hole pressure, pump intake pressure. So if we see this distance to liquid doesn't change, but the submergency, the gas-free submergency will be changing. The distance from the top of the liquid to the pump is not changing. That's 6644, but how much of that is actually liquid? Well, that's around 2,100 feet. It doesn't matter where you stop this test. It's very close to 2,100 feet, which give you the same bottom hole pressure, and that's what's important. Now, when you don't have such a linear buildup, that's when the problem comes. So your job, when you go out to acquire data, or when you come to analyze the data because you're receiving the data from the field, yes, you check the liquid level selection, you check the color count, but you also check how linear, how good is your pressure buildup. Is that pressure buildup representative for your well? So after the break, we'll come back with an example of a terrible pressure buildup and why you should pay attention to a pressure buildup being linear when you're analyzing fluid level data. Okay, well, welcome back. Looks like 5 minutes goes flying. And we were talking about going and check another example of a good fluid level measurement. Distance to liquid calculation would be okay. So let me go to that well real quick. And we have this fluid level shot. Again, fairly simple analysis. We have a down kick. It's just a down kick from the liquid level. There's nothing else. We have good color echoes. We have the color count line close to the liquid level line. So it means the software has done a good or decent job counting colors. We can see the color echoes. We see more colors down there. If you want to check what the color count was 94% of the colors counted. That's great. So that's not the end of your job. So you can't, or you shouldn't just go ahead and print the report because the distance to liquid is good. There are things that you need to check in addition to selecting the liquid level and having a good color count or whatever method you're using. If you are using this information to calculate buttonhole pressure or understand how much pump submergency or liquid above the tubing you have, it's important to check the pressure buildup test. And look at this pressure buildup. We can see the points are all over the place. That is a problem for your calculations. The software, again, will use this information to calculate bottom hole pressure. The software will use this information to calculate how much pump submergency you have. Let me go. Putting that information here. So we have this well. And if we look at the report, we see the fluid above the pump, after we calculate the distance to liquid, the fluid above the pump is close to 2,000 feet. And that's using the normal 2 minutes of pressure buildup. But what if you had stopped this test before 2 minutes? What if? So let's look at that. And we can change when we stop the test. So let's say you stop the test at, let's say here. So by stopping the test a few seconds before, the pump submergency, the gas-free equivalent, goes from what, 750 feet to 1164. So all of a sudden, we have 400 feet of pump submergency in the well. And that could be a problem because the pump intake pressure and the producing butthole pressure has changed dramatically. So we went from 436 to 600 psi. So how much liquid you actually have above the pump? Is that 1164 or is that 750? What if this technician was in a hurry and he only collected data for 30 seconds? Having a more pressure buildup according to the software calculation means you have more gas production, less liquid content. So liquid percentage went down to 27%, resulting in 540 feet of liquid above the pump. So you have a pump submergency of only 336, or pump intake pressure, 358 of producing butthole pressure. What if this technician was in such a hurry and only collected data for just a few seconds? Look at the jump going from this point to this point on the pump submergency. So we go from 541 feet to 1,700 feet. So all of a sudden, in 15 seconds, we have a difference of close to 1,300 feet of pump submergency. I'm pretty sure that if you're trying to optimize this well, if I tell you your well has close to 1,800 feet of pump submergency, or your well have 500 feet of pump submergency, your recommendation for your well will change. So it is important that the pressure buildup data makes sense. Is that according to your gas production in your well? Does that make sense? If you have a pressure point like this, you have to shoot again. You have to look for a more representative pressure buildup, something more similar to what we had in the previous examples. So if you import the data, you will have examples that has a more linear fluid level, and that's good because most of the wells will actually have a better pressure buildup. So having a buildup like this one is representative, and the other examples too. In this well, it doesn't really matter how if you stop it at 1 minute or 2 or 3, it will be the same calculation. To recap and close this topic, selecting liquid level gives you time. We will use one of the methods to calculate acoustic velocity. We're now talking about method 1, using the color count. The C line will represent the last color, and the software has done an excellent job counting colors. If you have input the right average joint length, the software will be calculating a good distance, average acoustic velocity. Now with velocity and time, the software will calculate an accurate distance to liquid. With a good distance to liquid, you know the pump submergency is, in this example, 5747. With a good pressure buildup, a representative one like this, the software will now have enough information to calculate the gas-free pump submergency. And with that amount of liquid above the pump and the perforations, the software will then calculate the bottom hole pressure of this one. Okay. If you have a pressure buildup like this, the software will have also a consistent result, and we may have other examples too. So next topic, what's next? Well, let's talk about a different method. What if you have something else, not just the liquid level kick, that you can use as a reference point? So we call using that kick a downhole marker. And we can use a downhole marker methods to analyze the well and determine the acoustic velocity and distance to the liquid level. So this method will depend on if you can include in the software different changes in diameter, like a tubing anchor, or what are those reflections? Well, that can come from different markers or from different changes or anomalies in your well. What is a downhole marker by definition? Well, it's a kick, it's a visible kick, it's a kick or a deflection or reflection in the acoustic trace that is above the liquid level and that you know the depth. So it has to be, again, a kick different to the liquid level, so something above the liquid level have a known depth. And the software will list what could possibly give you a kick in the well based on your well description. If you have input a detailed well description, like if you have different tubing sizes, casing sizes, nipples, perforations, anchors, packers, all this hardware in the software, in the hardware in the well, it'll give you a list of potential markers depending on if you're shooting down the tubing or the casing angles. Then the software will use that marker, the time to that marker, and the distance you have assigned to that marker to determine the acoustic velocity. Things that could be a marker in the well. Well, any change in the cross-sectional area caused by, for example, a tubing crossover, a tubing anchor, a casing liner, an end-up tubing, or an end-up casing. If you have an end-up casing, a casing chute to open hole, or if you have an end-up tubing to only casing, any perforations, if you have a gas lift well, any gas lift mandrel, if you're shutting down the casing, if you're shutting down the tubing, it must be a side pocket mandrel because they have a bigger ID. Any nipple, packer, essentially any change in the cross-sectional area in the well. If you have a casing patch, that is causing that. If you have any casing weight change, because the ID is changing of that casing. So any of that will give you markers. So if you have a detailed well bore information, you have to input that in the software to increase the chances of utilizing that information for the well analysis. So we have this fluid level. We shoot a flue level. The liquid level kick is clear, but we have a poor color count. Look at where the C line is at. So we have a poor color count in this shot. What we can do? Well, the recommendation would be go and shoot with more pressure, or too late. The data has been already sent. The guy is gone from the well, and you have to interpret the data. What options you have then? Well, looking at the trace, I wouldn't like to use a color count because the color count was poor. The software could calculate a good acoustic velocity down to the color count distance, but I don't know how the acoustic velocity behaves beyond the color count point. So I have too much uncertainty in the acoustic velocity down in the lower portion of the well. So can I do something else to analyze this shot? Well, looking at the trace, we can see that little kick that's coming from the tubing anchor. That's a kick above the liquid level, and it's a known depth. So do you know where the tubing anchor is at? Yes. You normally know where's the tubing anchor. You normally know where's the casing liner, the perforation. So you know that information. We can use that as a reference point, and we call that again downhole marker. By telling the software, now I'm not going to use the default method color count. I'm going to switch from color count to a downhole marker. And that marker is at 5122. So let's look at some examples of using downhole markers with real data to explain what the software does with this. So let's look at this data here. This is an interesting flue level shot. And we have more kicks down the well, but let's focus on this one. It is important to input a detailed wellbore schematic. If we look at that well, we have a tubing size, and then we have a change in size. So we have a tubing ID that's a tubing size that is changing right before the casing liner. So we have a smaller tubing ID at some point, and then we have a casing liner in the well. If you shoot a flue level and the flue level is below that tubing change in diameter and the casing liner, we would have kicks associated to that. Let me decrease the opacity of that flue level, of that wellbore. So we have the acoustic trace, and we have a small up kick. Why is that a small up kick? Well, the tubing is decreasing in diameter, which represents an increase in the casing annulus cross-sectional area. That gives you an up kick. And right after that, we have a down kick from the liner top. If the software uses a color count, the color count stops right here where the top liner is at. And I don't have more than 80% that I want. Then we have a liquid level kick, and we have an up kick. Well, what is that up kick? Well, that up kick, if you remember the previous slides, is the wave traveling from the liquid level back to surface and seeing the casing liner. So going from the casing from the liner to the casing. That's an increase in the cross-sectional area. So we have a down kick from the liner, a down kick from the liquid level, that's the liquid level right there, and an up kick from the top of liner. There are tools that you can use to determine distance or time difference in between. So we have a liner that is at 8.9 seconds. We have a liquid level that is at 11.2 seconds. So we have about 2.3 seconds in between. So time from liner to liquid level is about 2.3 seconds. So 11.2, that would be about 13.5 seconds. So the up kick is actually at the same time difference. So time from liner to the liquid level is the same time from liquid level to liner. We have other tools that we can use in annotations. Let me turn off the depth reference and use the fold trace. What the fold trace option will do is any acoustic trace below the liquid level line, it will be folded to surface. So if the time difference from the liner to the liquid level is the same from this to this kick, this up kick will match the down kick. Let's see if that happens. So when you click on fold trace, yes, that up kick that was folded back to surface, the up kick matches the down kick from the liner top. This is a quick way to confirm that this is just the liner repeat from the liquid level. Easy to use, but we don't want to use a color count. Let's better use a downhole marker because we have markers to use. Actually, we have a couple of markers. Let me click on method 2. And what we'll be doing is, we can use a tubing ID change, or we can use the liner top. And the liner top is actually there. You have the options to filter the data. So in fine tune, you can remove the filter or apply the filter. In this case, I like to remove the filter to better select the liquid level. But also, when I'm analyzing the acoustic trace, I can locate this line. So by clicking the liner, the software knows the distance. It's my job now to move the line to where I think is the liner top. And I think it's right there. So with that, we have a yellow band, and this thing here is a zoom in. So we can fine tune, let's sort of find the marker position by using this lower box. So now the software have distance to the liner, that's from your previous well input. And by moving the line, the time to the marker is adjusted. So the software has distance and time, and that's feet per second. It could be meter per second. So feet per second is actually velocity. So the 1268 are calculated based on, again, the distance to the marker you have selected and the time where you locate the line at the marker kick. With 1268 as an acoustic velocity and the time to the liquid level, the software now knows with very good level of accuracy that the liquid level is at 7,082 feet from surface. Okay, that's one example there. Let's check another well real quick. Let's use this other example as a downhole marker position. Okay, now we have a liquid level. We have not a bad color count, so we could use other shots, but this is a good one. I don't need to use the color count because we see that marker. We see the down kick and we see another shot. Yes, right close to 10 seconds, we have the down kick. So every time we shoot a fluid level in this well, close to 10 seconds, we have a down kick, and that is coming from the tubing anchor. Actually, we see this shot here is a poor color count, but we can still use the data to determine distance to liquid. Liquid level selection, again, is good. And you could have or not a repeat of that. We don't need it. We don't want to use a color count because it was really poor. And instead of doing that, we are going to use a downhole marker. So which marker can we use? From top to bottom, above the pump, we have a tubing anchor. When you click on tubing anchor, by default, the software will drop a red line, which you have to move, and it will drop it just somewhere at 1,200 feet per second. It's your job now to move the line to the marker depth. Just drop it somewhere close. You can always increase the scale. You can manipulate this to better select it. You can see less of the data. Increase that, and you're going to do a very good selection of this marker kick. So you have a down kick from the tubing anchor has been selected. This is the time. This is the distance. The software calculates velocity. With that velocity and time to the liquid level, we have a very accurate distance to liquid level calculation because we have the reference point. We know it's somewhere below that. This is a very simple method to use when you know, but it's important you input the details in the well. Okay, last, what's next? Let's change the scenario. So this method 3, we call it acoustic velocity, is used whenever you don't have other methods to work. So when you don't have colors to count, for example, you don't have tubing in the well, you're shooting down the tubing and you don't see the color recesses. You have just, as I said, no tubing in the well may mean that you are drilling the well and you don't have any drill pipe in the well. You have a flowing gas well, or you're shooting down the tubing. So you may have no colors to count. When you're drilling and you have a section, and that's actually coming from one of the questions, if that you can apply, if you have only a section of pipe in the well, and the fluid level is below the end of the pipe, so you have some annulus between the pipe and the casing, and then only casing, you can use the end of the pipe as a downhole marker because that will be an increase. So you can use that increase as a downward marker if it's not too far from the liquid level top. Now, let's say you don't have any tubing, or you're shooting down the tubing where you don't have any colors to count, but also you don't have any marker, because many flowing wells, you see some perforations, and you can use those perforations, or you see a liner top. So you have some kind of a marker that you can use. But in this scenario, when you have no colors, when you have no markers, then you have to go to the method 3 as an alternative, as a last option. So you have a couple of options here. You can manually enter the gas gravity value, or if you have a gas composition, a gas analysis, a gas chromatography, then you can enter the detailed gas composition there with all the percentage of C1, C2, so methane, ethane, propane, CO2, nitrogen, H2S, and so on. So you can input that detail of information, and I will go there. Let's put this in a worst case scenario. As the last option, the user could manually enter the acoustic velocity. So we have studied a couple of methods to calculate the acoustic velocity, but now we can, even if we don't have a way to calculate that, the software still needs an acoustic velocity. So you can manually input that. In this case, the software will allow you to manually enter, and you tell the software what is the acoustic velocity that you want to use for that fluid level shot. But that will be like the very, very last option you want to use. So real data, you shoot a well, you have a liquid level shot and a clear, a liquid level shot and a clear liquid level kick. So we have the shot, we have the liquid level, but there is nothing in between that we can use. There is no colors to count, and there is no markers to use. So what options you have? Use method 3. So when you go to the software and you click on method 3, this window will come up. And you can calculate what? We can calculate the acoustic velocity based on the gas gravity. You can just manually input the gas gravity, or you can go ahead and, input the gas composition. So you will have a gas analysis, and I have an example with that, to compute the gas composition from the gas chromatography. So the software will use the gas gravity, will use the pressure that is being measured by the pressure transducer. If you don't have one, you can input that, but normally you have a pressure reading from the sensor, and you have a temperature input. So the software will basically look at the environment where this wave or sound wave is traveling. So it will be, what is the environment? What is the gas composition that is traveling through? What is the gas pressure? And what is the gas temperature? So gas gravity, pressure, and temperature are the 3 factors that affect how fast the sound travels in that specific environment. That's not something you control. You can put more or less pressure to have more or less energy, but it's not going to make the sound to travel faster. The sound travels at its speed based on the environment. We're just providing enough information to the software calculate what is the resulting acoustic velocity. And it's very sensitive to the gas gravity. So you don't want to guess the gas gravity. Also, you don't want to use a gas sample to calculate the gas gravity. That is a gas sample taken from the sales point or after the separator, because that gas composition is not the same gas composition that you have in your well. It's important, if you're using the gas gravity, it should come from a sample from the wellhead, not down the road and their facilities. The software will use that information to determine, based on the gas gravity, pressure, and temperature of those lines, to calculate what is the resulting acoustic velocity. And it's very sensitive. I told you, 0.6 gas gravity with 400 psi at 108 Fahrenheit degrees results in 1,400 feet per second. Same pressure, same temperature, but a much heavier gas, the resulting acoustic velocity will be even less than 800 feet per second. So that's kind of a two far ends of the range, but this will be highly affected by the gas composition. So you don't want to just guess it. When you enter that information, gas gravity, pressure, and temperature, in the background, you don't see that. The software is calculating the resulting acoustic velocity. That's what the software is doing with that information. Last option, let's say you don't have colors to count. This is the worst case scenario. You don't have colors to count, you don't have any marker, and you don't even know the gas composition, have no idea about the gas. So the software still needs an acoustic velocity. What we do then we're going to tell the software, hey, I want to input the gas composition. I want to input the acoustic velocity because I don't have any means to calculate that. So you'll be using, if you click there, the software by default will show 1150, but that 1150 is just a software default. It doesn't represent your average in your area. So what you should do is, if possible, if you have historical fluid level data from this well, look at the data. Check if you had calculated before acoustic velocity from this well. If so, then use that information. Let's say, no, even worse scenario. You don't have colors, you don't have markers, you don't have gas composition, you don't have history of this well. Well, at this point, I think your only option is look at the neighbor wells. Check if you have collected data in surrounding wells that are producing from the same reservoir, which means the gas composition is pretty similar. Temperature in the formation is about the same. Surface facility are handled, normally having average surface pressure. So you have similar conditions in neighbor wells. So the acoustic velocity that has been resulted from those shots, you can bring it and type it here and use that acoustic velocity for your well. And that's probably the worst case scenario. Okay, so let's look at some examples of this gas gravity or method 3 calculation, and then we'll jump into some questions and answers. We go to the software and we're going to pick a different well. So we'll go and see, let's look at this example. This is a gas flowing well. We have a fluid level shot. There is no colors to count because this is a tubing shot. And we see a liquid level kick. First thing to notice, we know for a fact that the liquid level is not below the end of tubing. Why do we know that? Because if the liquid level is below the end of tubing, from top to bottom, we would see an increase coming from the annulus to only casing, or if you shoot the casing, or if you shoot down the tubing, which is what you normally do in a gas well, you shoot down the tubing, you go from inside the tubing to the casing. So the first kick that you could observe, if the liquid level is below the end of tubing, that kick would be an up kick because that's an increase in the cross-sectional area. And then after the up kick, you see a down kick. That is not the case. So when I shoot a fluid level down the tubing and I only see a down kick, and actually it's a large kick and you see a repeat of that at close to 27 seconds, okay, we have 13.57, so 17.1, we have a repeat. That's just a repeat of the liquid level. There is nothing in between. So there is liquid inside the tubing somewhere. What can we do? Well, we can't count colors because that's a tubing shot. We don't see the color recesses. We don't have any downhole marker. We don't see any marker that we can use here. The only marker is the end of tubing, and it is not visible. There is nothing. There is liquid inside the tubing, so we don't get to see the end of tubing. The energy reflects off the top of the liquid, so we don't see the end of tubing. So we don't have a marker to use. So we go ahead and use method number 3. So we say, I'm going to calculate this acoustic velocity based on what? Based on the gas information I possess. So you look at your well files, you go to your lab and you check the gas sample and you get the gas chromatography. You can come here if you have that access. You enter here to click on compute gas the gas gravity from the gas composition, and this is what you read from your file. And actually, I think I have the file available. Thought I had it somewhere here. So this is the gas analysis I was using. So you go to your lab and then you get a gas sample and you receive that information. Then you enter that in the software. With that information, the software will calculate the gas gravity. Now, the gas gravity is input with some contaminants. You have the temperature input, which again, this is just the software default. You have to get with your reservoir department and see what is the formation surface temperature, not the ambient temperature. So the formation temperature at top, and what is the bottom hole temperature, and also the pressure that you allow the pressure transducer to reach some pressure. So we have enough information now to calculate what? To calculate the acoustic velocity. Now, the software knows 1423 is coming from the gas composition and the time to the liquid level. Now we have enough information to calculate distance to liquid. It's important to have a good gas composition value. It's not enough to say it's about 0.59 or 0.6 or 0.7. It's between 0.6 and 0.7. Well, let's see what would happen to the 9652 feet per second if you just go ahead and say, I think it's around 0.7. So we go from 9652 to 8698. So we have 1,000 feet change just because of 0.1 change in gas gravity in this well. So we have here a big impact on the distance to liquid level calculation based on a wrong input in the gas gravity. So again, I think the message here is, the point here is, you must have, you need an accurate gas gravity if you want to use method number 3. That's why we put this as the last option. And in many cases, if you're a gas producer, that's probably the only information you can input, because you don't have, your fluid level shots will look like this most of the time. But if you sell gas, you normally know your gas. So they have a much better chance to know with better certainty, with more quality, the information from the gas composition. So they will know that, and that's the value they can use with a good level of certainty as well. You have that information, then the software will use that information to calculate pressure at the tubing intake, and you can do static shots. And we're not talking about the static fluid level calculation in this session. We don't have enough time for doing that. If it's a producing shot, we have a distance. The software will calculate the tubing intake pressure and the producing bottle pressure. And if you have static pressure and production data, the software will have enough information to calculate potential, which we don't have in this well. Let's look at another example. We have another use of the equipment is when you have regulatory shots. So this is another example. There is no tubing in the well. It's just casing. You go and shoot a fluid level. Most of the time you have shallow liquid level in these wells. You don't really need a lot of pressure. The wellhead is pretty much dead. In this case, it's only 3 PSI. So you're not expecting to have a buildup because the well is not even a producer well. And you have only casing. As you can see here, there is no color to count. There is now consistently color kick, so that's poor. We don't have any marker to use. There is nothing, there is no outstanding kicks above the liquid level. We just see the liquid level and it repeats, same time difference, all down kicks, decreasing in amplitude. So very simple liquid level. And we have that. With this, we now have to use the method 3. We don't have a gas composition, but this well is open to the air. Okay, so we don't really have any pressure. What we have in the casing is actually air. There's no gas or nitrogen injector or anything. So we know the acoustic velocity will be around 1150, 1140, 1170s is hotter, and that will fluctuate a little bit based on temperature, but you can, and this is one scenario where you don't know the gas composition, and this is by default in the software. So like 88% methane and then all heavy components. So this is not real. We can enter the acoustic velocity, and again, based on temperature, you can slightly adjust that, but it's not going to make a difference or important difference. This is a shallow liquid level. So 1122 coming from a manual input will be a very good distance to liquid calculation. Okay, we have a few more comments or topics here to discuss. So let me go through that real quick. There's just a few slides that I want to check, and I have used some of those. So one of the important features that we have included in TAM is the ability to overlay fluid level shots. You can go to annotations and go to click on previous shots, and you can compare fluid levels. You can start turning on different fluid levels. So when you click on previous shots, you will have a table with all the fluid levels belonging to this well. So you can overlay the fluid level shots, and you can align the fluid level by time or depth, depending on what you're looking for. Preliminary analysis, I usually align by time. And if I have calculated already distance to liquid, or sorry, acoustic velocities, I may align this by distance, but this is an example of overlaying fluid level shots. If you have weird kicks, abnormal noises, you want to see if that's actually a kick coming from the well or just an occasional noise. Like this little kick you can see the down kick from the anchor is on every shot, and the liquid level hasn't moved much. So actually you see a down kick in the black line, down kick in the blue line, and the red line is an up kick. So the liquid level in this shot, red line means that was earlier, before they stopped the well, they could see an up kick from the perforation top, and then the liquid level was below. After that, the well was stopped. And then you see a liquid level coming up to surface. So you can track how the liquid level is moving. You can do multiple things comparing fluid level shots. We have perforations. You have seen me using the reference line. So we have a depth reference line. If you turn on the depth reference, you can move that little dash line, and that'll give you the time on the upper plot and also the equivalent depth to that point. Like this well is a cold bed methane well where we can see 1, 2, 3 sets of perforations, and we can use that as a downhole marker for the analysis if you want, but you can also move your depth reference line. That will be pretty close to the perforation top. So you can look at that, and we have input enough information in the software to see detailed perforations. So that's a quick way to confirm that is not a hole in tubing, that is not a hole in casing, that's just a perforation as expected, but you have to have the well details. Fault trace, we did that with this example specifically. So we have a liner top, liquid level, and we see a liner repeat. When you click on that fault trace, you will see the trace folded up to surface where the up kick matches the down kick from the liner top, just as a confirmation. After that, you can remove it and they will look back again as it is. Another important feature when you're analyzing, especially for multiple kick wells, is overlaying the wellbore schematic. And I will probably move up to the list. This is really important. Understanding these kicks is much harder just going and trying to understand that from a piece of paper where you have the well file, or if you just overlay the wellbore schematic, now you see the drawing where the tubing anchor is at, you have that kick matching to the tubing anchor. The down kick is actually the liner top. You see another down kick, that's actually a gas separator. This well has been shut in and pushed the liquid level down. So it's a bigger tubing OD at the end. We see that as a decrease in the annulus area. And then we have a big up kick. What is that up kick? Well, that's the end of tubing. Well, you can see all those details much easier when you overlay the acoustic trace and you have multiple markers. One thing we recommend to do when you have multiple markers is to use the deepest mandrel. In this analysis, you could use the tubing anchor, the top of liner, even the separator, but you would have an acoustic velocity that's more representative when you use the deepest mandrel in your well. And we'll see a lot more of that day 3 of this session when Justin covered the gas lift section. So using the deepest mandrel, we, in this case, deepest marker, we have the average acoustic velocity, good determination of distance to liquid. We have a down kick from the liquid level, and then another down kick when the liquid level enters the annulus, because that's a decrease in the cross-sectional area. So very helpful thing. Understanding well problems, troubleshooting is a good part of it. So we have a fluid level shot and you shoot again, you clearly see a liquid level, but you see a down kick that is repeating there. If you match this information with the dynamometer card, which we will talk tomorrow, you may be facing a hole in tubing in a pumping well, where the fluid is partially full of liquid or full of liquid, but the liquid is coming from the tubing to the casing annulus. If you stop the well, allow the tubing to drain, you'll see something like this. At the same depth, you will now have an up kick, because in the annulus, you will have liquid coming from the tubing to the annulus, representing a decrease in the annulus area when the pump is running, or when the pump is stopped and the tubing empty to that hole depth, you will see the hole as an increase in the cross-sectional area in the annulus. So this is a good way to identify holes in tubing or tubing leaks in rod pump well, if the fluid level, of course, is below the hole depth. If the fluid level rises and covers the hole, you won't be able to see it, but if it's a shallower than the liquid level well hole, you will be able to see that. Last couple of slides talks about basically control quality, controlling the quality of your shot. So if you shoot a fluid level and you don't see a good liquid level kick, one of the recommendations is to shoot with more pressure. Now I have a slide after that show that. So this is a liquid level. Shoot a liquid level, you don't see a clear liquid level kick. This was a shot with 200 psi. So if you have something like that, the recommendation is to put more pressure. And the well may have no pressure, so you're doing what's recommended. Start with 200 psi, but 200 psi was not enough here because you can't see the liquid level very clear. So you go from this shot where you don't even know where the fluid level is at. When you apply more pressure for the next shot, shoot again, and it goes from this to this. Now you have a much clearer liquid level peak. It's simple for the software to pick it now. And actually it was there before, it was so small that you couldn't see it. Now it's much bigger because the energy is more. So reflected energy from the liquid level is more. The microphone picks that echo, but also we can see colors all the way down to the liquid level. So it goes from a trashy quality fluid level because of the low pressure differential to a excellent fluid level shot. So you can do that. This is a PCP well where you can determine pump submergency very well now after increasing the pressure to 500 psi. We have other features as filters. We have a low pass filter that you can apply when the well is very noisy. And going back to this, you have to inspect the acoustic trace before you take a shot. Before you take a shot, before you click on fire shot, look at the acoustic trace, see how much background noise you have. Inspect for recurrent noises. Maybe you have a chemical pump running in the well, something creating a vibration, mechanical noise coming from a pumping unit or something downhole, couplings tagging the tubing, a wellhead, things like that that may be creating noise. So inspect the trace. Look at the background noise. See if it's too noisy. You may know in advance that you need to put more pressure in the volume chamber. Shoot the well, inspect the results. Do you see a liquid level? Yes. Can you count colors or can you see a downhole marker that you can use for that? If it's too noisy, maybe you need to stop the pumping unit. Sometimes, and only sometimes, you need to stop the pumping unit because it's so noisy that doesn't allow you to see that. If you have a gas lift well, it may look like this. This is a shot in a gas lift well with the injection open. And this is actually an offshore well where you have a subsurface safety valve and a couple of mandrels. And we go from this data where you pretty much you can't see anything, and you apply the low pass filter, and that's in the software here in fine tune low pass filter. When you apply that, we try to eliminate the high frequency noise. And after you apply the low pass filter, it goes from this to this data. So you can see some kicks, actually the deepest mandrel and the liquid level. So it goes from nothing to something you can perfectly interpret by using a downhole marker, and you can select the liquid level very accurately. So this is useful data after you filter it. That's one other option that we have to analyze the data. Connection matters. How you connect the gun to the wellhead, how straight goes that down the well. Remember, what causes echoes is decrease and increase in cross-sectional area. So how many changes in diameter we have here before we actually enter the well? Many. That usually results in noisy data. You see, it's kind of a dark, it's noisier, and it's going to be harder for the software to identify what is an actual echo from the color, if you're counting colors, or is an actual echo from this that's kind of ignore all this shallow, high frequency noise, all this resonance here, and identify colors. So try to connect the gas gun as straightforward as possible to the wellhead. Pumping unit related noise. You see, and actually you should catch this before the shot. So if you're looking at the background noise, you see an echo, you see an echo, you see an echo. Well, that's not actually echoes from the well. You see the amplitude? Amplitude is the same. It's the same size, the same shape every time. So if you see an echo, look at the pumping unit, look at the source of that noise, and you will know this is there before the shot, and it will appear in your acoustic trace. So you can ignore that. But if the liquid level kick happens right in the noise time, you may have difficulties identifying the liquid level. This for sure will decrease the quality of the color count. So in extremely noisy pumping units or noisy conditions, you may want to stop the source of noise. This is another example. You can see the same frequency of that noise, and it's usually around the same time. This goes from this noisy low color count. If you see the liquid levels here, the color count stops here. but actually after you stop the pumping in this one, the quality is much better. You can have a much better call account, but also you have some downhole markers to use there. And with 10 minutes to finish the session, we are open for questions. So Justin, what do we have there?
So far we have 6 questions, and I feel that throughout the presentation, most of them have been answered, but I do want to just reiterate and just focus on some of the questions that were asked. So one of the first questions that was asked is, can you change the units from standard unit of measurement to metric or whatever, custom measurement we would like to use?
Yes, and I've done some of that already, but let's do it one more time. So yes, you can always change, and you can do a general change, go into preference. So utilities, preferences, and then the first tab will be units. I'm using also units. You can use metric system, or you can have a hybrid. Like if you're in some countries like Canada, but for example, Mexico, they use both production in barrels per day, but distance in meters. Sometimes production in cubic meters and things like that. So you can customize the units here, or from the value itself. Like if we have distance, you can change that from feet to meter, or pressure values. Like we have PSI, but you may be using KPA if you're in the Middle East, or you may be using bars if you're in Europe or somewhere else. So yeah, there is a complete flexibility in the software to use different units, and it's that simple to change them.
Sure.
I hope that answered the question.
Yeah, I think that answered it right there. So the next 2 questions we can actually combine, because I think you can answer it with one answer. So one person asked, are the input parameters the same for TWM as they are for TAM? And then what input parameters are most important in order for the measurements not to be off?
That's a good question, very common, by the way. So what's important when you're new to this and you say, well, I don't have the complete information of the well, what should I go and request as a minimum to have a successful data collection? Well, there are some key parameters that you want to have, so the software can at least calculate some distance to liquid, calculate the distance to liquid, and also bottom hole pressure. So for fluid level shots, an Echometer can do different type of tests and acquire different type of data. And tomorrow we'll be talking about collecting dynamometer data. So there will be other requirements that will become critical when you acquire dynamometer data. But let's stay within the fluid level realm. So fluid levels, you need, ideally, if you have tubing casing size, that'll be preferred. But important, really important, formation depth. If you have a pump and you're looking for pump submergency, you want to input the pump depth so the software can distribute the columns of oil and water in the well, and the average joint length. It's important for you to input average joint length if you want to use a core account as a method. If you don't have tubing and you have like this example here, you just use the gas composition, then the gas composition becomes critical. If you have a gas flowing well, an offshore well, if you have a tubing and you're shooting down the casing, then the average joint length is critical. If you have a downhole marker, well, you need well details that tell the software where the marker is at. So if you have a liner top, or if you have a perforation that are exposed above the liquid level, that becomes critical, but that's something you want to use for the fluid level. That's on the critical side of the information. Again, perforations, pump, ideally tubing casing sizes, but more important, average joint length. Now, then you can put more information, more details like API gravity, water-specific gravity. Survey. The survey is really important if you're focused on calculating bottom hole pressure, because we are talking about hydrostatic liquid columns, and those hydrostatic columns will be affected by the true vertical depth. So if you have a deviated well, you have to input that. So that will be the most critical information, especially if you're looking for downhole pressure calculation. Now, let's go to what is difference? What is compare? How do we compare TWM to TAM? Well, TWM is really old, has very limited data input, and we can pull a detailed well file, and first you can input history of production. You can input multiple, and this well is a monobore well, by the way. You can input different templates, different type of wells. And let me pull a different well because we don't have casing in his, sorry, we don't have tubing in this well. This is only casing. This is a monobore well, so we only have a casing table. Any of our other examples will have tubing and casing. So on the detailed view, we would have access to the mechanical wellbore, and the tubing, we can enter multiple tubing sizes. And actually, we have an example for that, being that the production liner. Let me pull this. This is more complete one. So in this example, we have different tubing sizes. We have different casing sizes, which is totally different than TWM. TWM only allows one tubing size, one casing size, and you have to pick what to put. So that would be hard for this. Well, you can put a lot more details in TAM. So bottom line, TAM is a much more powerful. Survey is another huge difference. You can input a survey in TAM that is, it doesn't have a limit of points. Compared to TWM, you have to manually input 15 points. So you can input here 100, 200, 300 points survey, just copy paste. That would be quick and easy. TWM will have to manually input that. So there will be much better calculations. Production intervals, you can input different production intervals. So it's much more detailed. If you're using a wireless system, actually there is a wireless base. If you have wireless system, there is a wireless base that replaces the well analyzer. I'm showing that on the screen, the little yellow base that looks like a router that communicates from the computer to the sensors. It has a GPS installed, so you can tag the coordinates to that well. And every time you visit the well, the software will show a pop-up screen and say, hey, I detected this well around you. Do you want to use this well to pull the well file? So it avoids the error of shooting fluid levels in the wrong well.
One thing we'll do real quick as well, Gustavo, go back to edit and to survey. This will be a good point to mention is that, if you're using a software such as WellView or some data housing software, which you export the data to Excel and then copy and paste the true vertical depth and measured depth to paste it into TAM, is make sure that you put the numbers in general mode. Okay. TAM does not do well with commas. It does okay with periods, but it doesn't do good with commas. So make sure you go put it in general mode. So that way that you can get the data into the software correctly.
Yeah, like if you have this with commas, the software doesn't like that. So you go ahead and put them all without commas, just decimal points. And depending on the country, you may have a different regional configuration, but Excel can help you to change that real quick. So you can select all the points, and I'm just quickly going to copy a deviation survey that has close to 200 points, come here, paste it, and that will be just inputting the well deviation. Obviously, I'm not going to save this because doesn't belong to this well, but it's that simple to input that.
Yeah, it's definitely a lot easier with TAM versus TWM. Okay, so the next question we have is, this individual said, in a high water cut well where there's a water level, an oil, or I guess we should do it this way, where there's an interface between the gas, the oil, and the water, can I see the individual interfaces because of the density changes between the interfaces?
Okay, and we see some of that. We can see the interface from gas to liquid, but we cannot see below the top of the liquid. So we don't really know, like if a producing well, liquid above the pump to the liquid level top is usually 100% oil, and below that is mainly water. If that's the case, you know where it is, but you cannot see that on the acoustic trace. The echo that you generate from surface, like pressure wave, will reflect off the top of the liquid, but you don't know what's below that. It may be a total blockage. Even if you have a packer, you can see a gas solid liquid interface, a gas solid interface, but that's a total blockage, and that's what the liquid level is. The liquid blocks all the cross-sectional area and reflects all the energy back, but we don't know what's below that. So we see the gas liquid interface, but we don't know where the other interfaces are below the well.
Correct. Okay, I have two more questions, and we'll go a little bit longer than 11, but it's okay.
We have a minute. I'll go quick on that. Go ahead.
Okay, so is it possible to take a measurement where some of the tubing is pulled out of the well? What average tubing length would I use?
Did you say a portion of the tubing or the whole tubing is out?
Correct. Can I take a static measurement in a well where a portion of the tubing has been removed from the well? And if so, what average joint length would I use?
Sure, that's great. So if you have a portion of the tubing out of the well, that's actually great because you will have the inner tubing. Well, you would, if you want to use a color count, which I don't see why you want to use a color count, you look at the portion of the tubing that's still in the well, and you can calculate the average joint length for that. But what I would recommend in that scenario, and that's very common in workovers or drilling operations, where you're pulling out the tubing or the drilling pipe, and you stop somewhere, you can shoot a fluid level. Then you have that downhole marker because you have the end of the pipe, and you have that increasing cross-sectional area that you can use as a downhole marker. So instead of using color count in that condition, what normally used is a downhole marker method. Hope that answered the question.
Yeah, for sure. Okay, and finally, the last question is, this is going to talk about best practices, which I want to point out before I read the question. We also have a Ask Echometer session about best practices for shooting acoustic fluid levels from the website that you can look at to get more details. But is it a good practice to bleed gas from the well prior to installing the wellhead attachment? Go ahead and
talk about that.
Yeah, I sure can. So ultimately, any change in cross-sectional area is going to cause a blockage. And so, it's very common that prior to installing the gun on the wellhead, operators will crack the valve and blow any grease, debris out of the valve before installing the gun on the wellhead, just to keep the debris and trash from the well from getting into the gun. It's very common practice. Purge it real quick, obviously keeping in mind what your gas content is. If you're at 1% H2S or higher, or you're not going to do that. However, it is common that people will clear the valve prior to installing the gun so they don't get trash and debris inside their gun.
And a quick bleed for cleaning purposes is fine. What is not recommended is to bleed the well. So some people find you get to the well, you have pressure in the casing or the tubing, and you open and bleed the pressure down to the line, or sometimes it's even worse to the atmosphere. We don't recommend that because what you want to have is a picture of what's going on in the well, and you don't need to bleed the pressure. You have working pressure high enough in the gas gun where you can shoot above that casing or tubing head pressure. So we don't recommend to bleed the pressure to shoot the fluid level, maybe just for cleaning purposes if you're aware that you have blockage where you install the gas gun.
Correct. And then the second part of this question is do I turn off the well in order to acquire the data, or do I just start recording? Well, the answer to that is it's very hard to measure something without changing it. How I like to approach it methodically is that, say I'm shooting a rod pump well. I would like to install the gas gun and put adequate pressure in the gun and fire into the well and see if I can get a good fluid level measurement with a good collar count, or see downhole markers which I can use. My last resort is going to be turning off the well and actually changing the condition of the well for a measurement. I'm going to use other ways. I'm either going to increase the charge pressure in the gun, or I'm going to rig up on the well, get ready to go, turn it off, take the measurement. And so that way I affect the measurement as little as possible. Okay. But there's other things that you can do. Now, for example, we had a slide that showed pumping unit noise. If you're unable to get a good collar count or calculate good acoustic velocity due to an external noise, which brings up the point of turning off chemical pumps and turning off any source of noise that may interfere with your acoustic shot, then ultimately you may have to turn off the pumping unit. However, you want to take the measurement though with the well running if possible. It's kind of my modus operandi as far as approaching a liquid level shot.
100% agree with that. It's recommended just get to the well, take the picture as the well it is, shoot the fluid level without stopping the pumping. If you see noise level is too high, you see recurrent noises, and then you need to stop the pumping unit because of that. Because after you try everything, you couldn't still have a quality shot, then that's okay. Stop the pumping unit, shoot the fluid level right away after the noise level decreased, and start it back again. So it will be just a couple of minutes down, if that much.
Okay. And finally, the last question that actually just came in, and it's, can a tubing or casing leak be detected with a pressure buildup feature in the software? Now, I'm going to go ahead and say that it can be detected. And whenever we get to Wednesday, when we talk about gas lift, we're going to talk about a method that's called the dual shot method. in which we will talk about finding leaks and leaking gas lift valves, leaking check valves. And so that's kind of foreshadowing into Thursday. But it also can be found based on the direction of kick. You know, Gustavo talked about how an increase in cross-sectional area with an explosion shot leads to an up kick, whereas a decrease is a down kick. And so it can be found with the acoustic trace. You put in here in the question, can it be found utilizing the pressure buildup in the software? Well, there are certain conditions, whereas maybe if you have a packer, or you can utilize the information of pressure buildup to potentially point out communication. Is it going to tell you where it's at? No, you'll need to rely on the dual shot or the acoustic trace to do it. However, if you think through methodically how we're going to utilize this pressure buildup, yes, you can use the pressure buildup feature in the software as long as it doesn't exceed 15 minutes in a normal acoustic cycle. There are other things we'll talk about, plunger lift, where you can stream data. It is being used and it has been used. But you can really get creative, and if you get creative in the ways that you're utilizing the software, that's something that we want to know about. We'll talk more about that in the dual shot on Wednesday, but we want to know about how our users are utilizing our equipment, because that's the way we make it better for everyone.
Yeah, that's a good point. We will need to understand more what type of well are they talking about. Are they being able to manipulate the pressure by injecting or bleeding some of the pressure, monitoring other side? If it's through a single shot, you have mentioned, Justin, that you only have a 15-minute window of pressure data collecting. If it's just using the liquid level single shot method, or if you have a plunger lift license, your well analyzer, or wireless base, then you could use a plunger lift module to have a longer pressure track in either the tubing or the casing. So it could be done. There are special techniques that are used to identify tubing casing leaks, and that'll be covered in 2 days. So stay tuned for Thursday. And we appreciate all your participation. I think it went very well, and we appreciate your comments. So we'll be following up with an email where we will share the presentation, and hope to see you tomorrow and after tomorrow here as well.
All right. Thank you all for attending.
Thank you very much.